Okay, the registration started. Gabriele, I am not yet host. Now I am. I may be able to give to Lorenzo the cost privilege, but I don't know how to do it. Okay, cost is I give to him the responsibility to keep the meeting on if I go offline for some hurricane. And I have seen also road stabbings connecting with us, and Meredith Joyce in this moment. Road stabbings is the most prolific observer in AAVSO that I know, and that I know he is alive because he's there. He's from Australia, and he has helped me in following Betelgeuse during the month of June, because in Australia you can observe it in the beginning of June, in the twilight. He has 350,000 observations. Isn't it, Rod? I think he can ask, he can see us, but not sure if he heard all what I said. Okay. So I think we can somewhat start because, oh, ecco, Rod, welcome to our meeting on Betelgeuse. The procedure is to unmute. I think we can unmute ourselves by clicking here. So I am not mute now, but so I have to do that. And if you want to intervene, you just click here and speak. This is the list for the moment of the attending people. I thank you, all the people attending now us. I saw that Rod is capable to speak. I was saying hello to you and telling that you observed the Betelgeuse during the month of June by eye, naked eye, while usually you observe with some other techniques to get 300,000 observations. And but now let me start with the presentation, so we can gain some minutes to the program, and in any case, someone connects later has the possibility to hear me again, because I have already registered my talk and I put it in this website. So in the chat, I try to communicate. No, I don't find the chat anymore. I would put in the chat this link, but for the moment, there is no chat. Annota? No. Okay. Well, welcome everybody. The title is slightly different from the title you have in the official meeting, because it's not rise I, but this one, which is kind of resurrection. We had this exchange of words with Professor Ruffini in January 2020, and I wanted to remember this with this title of my talk. This is the table, this table, where the organization of the meeting was going. And the 5W that I encourage every one of you to present while present your talk. I am Costantino Sigismondi, 1969. Why I studied Betelgeuse? I want to answer as George Mallory, one of the alpinists, died on the Everest. He said, because it is there. When I observed continuously Betelgeuse since 10 years, what visual photometry with air mass correction, where from Rome, Paris, Rio de Janeiro, at school, at university, on the street, wherever. Basically, Betelgeuse, besides our sun, is the brightest variable stars. Anyone can see Betelgeuse varying, provided that he knows how to do air mass corrections. VY Canis Majoris, which is another interesting star, I was impressed last GAPS meeting organized by Jacob van Loon in the presentation of Philippe Massey, looking this lecture on VY Canis Majoris by George Wallerstein. Look how many people attended this lecture. Now, VY Canis Majoris is well known even by the young people, but Betelgeuse should be the more known star in the sky. So the audience is potentially infinite. Before the telescope, another title of mine. I will be very, very short in saying the things. This is the Uranometria of Johannes Bayer, the lawyer interested in astronomy who published this wonderful map of the sky, and he assigned to Betelgeuse the letter alpha, which means the first star as magnitude in the constellation. Rigel is beta. Now, we all know that it's the contrary. Betelgeuse in general is less luminous than Rigel. The constellations made by Bayer on the paper are made in marbles in the meridian line of Santa Maria degli Angeli in Rome, one of my favorite instruments. Ptolemy classified Betelgeuse as magnitude 1 minus, while Rigel was magnitude 1, so brighter than Betelgeuse. Why? In 1603, Bayer changed the order, probably Purkinje effect, probably an outburst of Betelgeuse or its past history. Another image from the meridian line of Santa Maria degli Angeli, Betelgeuse, Bellatrix, they are nearly at the same zenithal distance, and you see their representation is corresponding to the dimension, their magnitude is corresponding to the dimension of the stars. And this is the sun exactly on the position of Betelgeuse, so in the month of April. This was the image I used to launch the meeting we did on January 17, 2020, to which, among the participation, were Margarita Karowska. And she also studied Betelgeuse since many years, and she contacted me for this occasion. So from this contact, the meeting came out. I mentioned Wolfgang Wohlmann as the author of this splendid curve, which is extended in the past for many, many years. In particular, the series in V-band with DSLR is at least 10 years long, while his observations last from 1976. But I want to mention Alexandria Morin, Rob Stubbings, who is connected with us, Ottmar Nickel, who will speak later, Fabio Mariuzza. I mentioned 2 times Rob Stubbings because of his 300,000 observation, Brian Kutnik, and so on. And many other observers, as Edward Guinan wrote, 6 generations at least of observers. How to observe? We need to do air mass correction. With this table, it is possible but complicated. With this one, with this quadrant, it's more simple. How? In this way. We print the quadrant, we put a line of sight, and we add a chord with a weight. And the weight, for example, at 45 degrees, the chord is in this way, says to us that we have 1.4 air masses and 0.033 magnitude of correction. This correction has to be done for all the stars, Betelgeuse, Aldebaran, Procyon, Rigel, Pollux, and so on. Also very far from it, because the problem of Betelgeuse is that is first magnitude and has to be compared with first magnitude stars that are not very close to it. That's why air mass correction has to be applied. The problem is even larger when we have to do with Antares, Aldebaran, Antares. Aldebaran is another problem, less variability. The ADSO database, Guinan will speak more about the analysis of it, but just a quick look on the big minima and the bright maxima. Our working hypothesis, we can see what weather is on Betelgeuse, like we can say the same thing on Mars. Is there dust, or the dust is behind it? It's difficult to observe Betelgeuse in daylight. This is an example of a photo made with the smartphone connected with a small telescope. And the problem is that in these conditions, it is difficult to have a comparison star. Can be a planet, and the planet is not a standard candle, especially if it has phases. So, interesting problem in visual analysis. I wrote a paper in the last day of 2019 saying Betelgeuse a minimum about to end. This was the motivation of the meeting I mentioned, 17 January, because the media were too much concentrated on the eventuality of supernova explosion. Now, obviously, if you don't speak about explosions, nobody will care about that. But in a meeting of general relativity, at least the basis of core collapse, and in particular of free fall timing, have to be known by everybody. But not only in such a meeting, I think in all high school. How long is the free fall time for a tensor masses nucleus? Kind of 5 hours. It cannot be 3 months. So 3 months for a typical behavior of stellar variability, even if it was particularly rare. Other stars are wherever. If we go in Rome, we can find the history of astronomy on in the place more relevant, and this is a phase of the measurement of the solstice that I made this year in St. Peter's Square. This image is like a moment of tour that is always present in the meetings, except in the case of online meetings, in which we cannot do that tour, and we are forced to attend sessions even of 7 hours, like today. The plenary session was from 6:30 to 13:30, 7 hours. Anyway, so finally, I presented very quickly my 5 contribution. Let's say the one entitled Fall and Rise of Betelgeuse was this one. It was basically the rationale of this parallel session. The other one regarding the history of astronomy pointed out the problem of Bayer's magnitudes. The other one about the didactic section explains how to do a good citizen science applying the air mass correction. It is very useful to introduce students to astronomy. The one about observations relies to the possibility to have a glimpse also on other stars, like the hypergiants Upsilon Canis Majoris, V766 Centauri, and so on, but in particular Aldebaran and Antares, that are visible without problems, but difficult to be observed without DSLR at least. And the problems of observing Betelgeuse at sunset and at sunrise. And the session structure you have seen, because you are also a speaker of this parallel session, so we'll deal with observation of Betelgeuse all year long, so also during the conjunction with the sun. The peculiarity of Betelgeuse we will hear soon by Jacob van Loon, because he sent a registration, so I think it is better to hear him before. And afterwards, the model of Betelgeuse, dynamical or numerical, stellar evolution, the observation, the analysis of time series, the observation with respect to the spectra, and finally, the 2 talk that are gathering probably the longest experience on this star achievable for humans. So my presentation is end. I just remember to you, please send me the presentation so I will by email, so I will put it in this website, the working website, always ICRANet network endorses of this session. And this is the image we took from Ostia Beach, Betelgeuse, at the same luminosity of Bellatrix on the January 22nd, 2020. So next speaker, please don't have, is Jaco van Loon.
Yes, it's a bit hard to hear.
Sorry, I heard some word. You can hear and see correctly?
We can see the presentation, but we cannot quite hear it.
You cannot hear? Okay. So probably it's a problem of microphone and
We can,
please?
we can hear you.
Okay, but not the okay. I can
No.
try.
No, we cannot hear the speaker. Jaco, we cannot hear.
Okay, so I will try again, putting the microphone close to the audio system. Let's see.
Ooh,
Can you hear?
no, apparently.
How to do, because before in the trials it was possible to hear him. Okay, another tentative is this one. Very scary. Can you hear? Can you hear him?
No.
No,
No.
cannot hear.
Okay. I knew that this was a potential problem for the. So better to start before than later.
Has this been pre-recorded?
Is pre-recorded, yes.
How do you share the computer sound?
That's the problem, because before I did share and the computer was working. The connection was verifica altoparlante micro audio del telefono, lascia computer audio. Computer audio.
As Sandip just wrote a message that you're not the computer sound.
You don't hear the computer sound, okay.
No, he's giving us, this is Sandip, George. He's writing to everyone. there's a site that you can go to. How do I play audio from my computer?
Yes, there is the site. So I
We could
can
do this. We could do the next talk and then figure this one out.
Yes, yes. So I would ask to Otmar Nickel to start his own talk. And by the time I send you the link where to hear Jaakko van Loon, and we will hear together immediately after Otmar Nickel. Okay? So I stop my condivision and I ask Otmar to connect his computer.
Ladies and gentlemen, Mr. Chairman, many thanks for the invitation to this meeting. I am a retired physicist, and my work now is the photometry of variable stars in my backyard observatory in Mainz in Germany. Since about 2 years, I try to get images of bright stars at daylight. The picture you see here is an image of Betelgeuse taken at noon on 19th of June when Betelgeuse was at conjunction to the Sun. This is a light curve of Betelgeuse in the V band taken by many amateur astronomers with digital cameras. Many of them are by Wolfgang Vollmann. He is auch in this session. Unfortunately, there are gaps in this curve when Betelgeuse is near to the Sun. That means at a distance of less than about 30 degrees to the Sun. To fill these gaps, there are 3 ways. One is observations in twilight close to the horizon, preferable in the southern hemisphere, or observations with space probes distant from Earth, e.g. the Stereo A space probe, which has already done some measurements, or observations at daylight. Here is my equipment. You see here the telescope of my observatory. It is a standard 10-inch Newton telescope on an equatorial mount. The mount is computer controlled with encoders in both axes. Images are acquired by a cooled CCD camera, which is in this white box. And with a neutral, with a V filter and a neutral density filter to reduce the light intensity. The front of the tube is enlarged to reduce stray light from the Sun. Here again are images of Betelgeuse on 19th of June. The left image is a single image with a 0.1 second exposure, which is very noisy. You see that on the profile. If 100 of such images are stacked together, the signal to noise is very good. Also, the signal of the star pixels at maximum is only 3.5% of the sky photons, which are seen here. This to evaluate the brightness of a star. Excuse me. The sky brightness can be measured in magnitudes per square arc second. Here are my own measurements shown as a graph. It depends mainly on the angular distance to the sun, which is shown here on the x-axis. It can be shown that stars can be imaged if their brightness in magnitudes is at least in the order of the sky brightness in magnitudes per square arc second. Therefore, stars up to 2 magnitudes could be visible near to the sun. To evaluate the brightness of a star, first an instrumental magnitude has to be measured. The logarithm of pixel counts here within this inner aperture corrected by the sky background here around is proportional to the star magnitude. The same procedure is done for one or more stars whose magnitude is known to get a standardized magnitude. One has to do also air mass correction to the calculation that Costantino has said already before. I did first measurements of Betelgeuse with only one comparison star, namely Aldebaran in 2020. In 2021, the methods was improved by using 4 to 6 comparison stars with brightness of up to 2 magnitudes. The upper diagram shows the 2020 light curve of Betelgeuse with the results of my first attempts for daylight measurements here seen on these crosses. The 3 red points are measurements of the stereo A probe. The errors of the daylight measurements were in the order of 0.07 Mach. Below there is the 2021 light curve, again with my daylight measurements seen as crosses. The gap of values could be now relatively well filled with data. The errors were less than 0.05 Mach, even at the closest distance of 16 degrees to the sun. There may be a light systematic error of 0.02 magnitudes seen here, whose reason is not yet known. I am in contact, therefore, with Tom Calderwood of the AAVSO to check the differences to the standard methods. To check the method at even lower distances, I made measurements on the 2 Mach star Alpha Arietis. There were no significant deviations of the results to the value of the Hipparcos catalog, which is 2.01 magnitudes. The individual errors were again less than 0.05 magnitudes, even at the closest distance of 10 degrees to the sun. In conclusion, Measurements of the V magnitude of Betelgeuse is possible with astronomical cameras at daylight, even at closest distance to Sun. The method gives reliable results with an error of less than 0.05 Mach, clear sky provided. The solar conjunction gap of the light curve can be filled if this method is used also by other observers. Thank you for your attention.
Thank you, Otmar, for this presentation. You remember to me that Rome tradition for observing in daylight the stars started exactly in the meridian line of Santa Maria degli Angeli, where the stars were observed during the day in order to compare the position of the sun. I see Edward saying clap to you, and I try to share the screen with this instruction that I thank Sandeep to have sent before, and we will try again to hear the presentation of Jacob.
Hello, and thanks, Costantino, for organizing this session on Betelgeuse.
Can you hear?
Yes.
Yes, yes.
Okay, perfect. So 10 minutes, go.
So what I will do is look at how the human psyche interacts with reality and time, where we try to make sense of Betelgeuse and red supergiants in general. So we can ask a question whether Betelgeuse is typical for a red supergiant. And you might think that it should be, because it's one of the nearest, and so they should be the most common. But that's not always the case. So we have had examples, for instance, supernova 1987A, which was the closest supernova that's been studied in very much detail. And it's not one of the most common types. Also, we have to place it in the context of the environment. So when we see Betelgeuse fairly near to the sun, we're not in a spiral arm. So this is maybe not the most typical red supergiant environment. On the other hand, Betelgeuse does not stand out in terms of luminosity, temperature, mass loss, quite moderate, or its dust content. And so in that sense, it's typical. But we can also look at whether Betelgeuse might be atypical in some way or another. And the first thing that comes to mind is its location and its space motion. So it's located quite far away from its birth site, probably. And the space motion is quite large, and that's also reflected in the bow shock that you see. It also has rapid rotation, and that's perhaps a little bit unusual as well, and nitrogen enhancement of the surface. And apart from that, of course, we have recently seen a great dimming. So is that atypical as well? Of course, it may have nothing to do with the above. However, no other red supergiant has been scrutinized in the same detail as Betelgeuse has, because red supergiants are rare, so you see very few nearby, up close. Of course, looking from the Earth at a star, we have a one-sided view. We only see the front facing us. And so if you're thinking about the great dimming, that happened, of course, on the side facing us. So how rare is this actually? So this is our bias. And just because we didn't see it before or elsewhere, that doesn't make it rare per se. For instance, here you've got a lamp. What would you conclude? That lamps are black, or that lamps exist that are black, or that lamps exist of which at least one side is black. And indeed, the latter is the truth, sometimes. We're talking then about non-isotropy. So Betelgeuse might not be isotropic in its emission, in its temperature profile across the surface. And so this is very important to take into account. Now, from imaging, we already knew that Betelgeuse is forming dust clouds episodically. That doesn't necessarily mean that it ejects a lot of additional mass episodically, but at least the formation of dust happens episodically. And if you look at these fantastic images that have been taken fairly recently, we're probing essentially a century of mass loss. And if you count kind of the number of blobs that you see, you come to the conclusion that dust clouds are forming every 5 years. And if you compare this with a dice, a normal dice, 6 faces, so let's assume Betelgeuse is a cubic shape, then of course we would only see once every 6 times such a cloud in front of the star. And so if you look at the light curve, of course we've had that great dimming, but in the past it has dimmed before, and possibly by similar amounts. And of course we would have missed some. So we can say that we certainly will have missed some great dimmings on the other side. Yeah, it's a certainty. It's not just that it may have happened. And a century, of course, is not very long in the life of a star. Yeah, and this is again our human bias. Even that of a red supergiant, which of course has a short lifetime compared, for instance, say to the Sun. But looking at the Sun, bringing it home, the Sun has been more dramatic in some ways. Looking at the sunspot cycles, for instance. Now, what if he had invented the telescope a century later than it did? Would we have known of the Maunder minimum, which is an extremely dramatic event in the sunspot cycle? So how common are anomalies in general? For instance, let's compare with Antares, which is a red supergiant at a similar distance, and in many ways quite similar to Betelgeuse. It has a similar, roughly, luminosity, temperature, convection pattern, mass loss, and also a low dust content. And even if you look at its light curve, it has similarities. It's rotating, but slowly. It's got a companion, a white companion, a hot main sequence companion. So you could say maybe it has some similarities in that sense to Betelgeuse or its past, but it's also a little bit different. So which one is more peculiar? So imagine stars are characterized by, say, 5 features, and each of those has a 1 in 10 chance of being anomalous. So let's roll a 10-sided dice. Let's roll it 5 times. Then you would have 1 in 2 stars which will show an anomaly in one of those features. If you roll it 10 times, then good chances are that the star will have shown an anomaly. And we also have to be very careful in looking at which features are correlated, which features are directly dependent on one another. So, for instance, here we've got a bunch of fluffy brown balls with beaks, and there's one that stands out. It's got a blue coat. It's not fluffy. It's got yellow cheeks. It's got an orange underbill, and so on. So it seems to have many differences compared to the other ones. But in fact, there's just one. It's an adult. So looking at those features of Betelgeuse, for instance, it's got fast rotation, it's got nitrogen enrichment, but those could be directly linked. So really, it's one feature. It's isolated in space, relatively. It's got a bow shock, it's got a high space velocity, but those are linked. And that and the fast rotation and nitrogen enrichments may also be linked through binary interaction, for instance. So in a way, that's just one common feature. And studies have shown that about a third or so of all massive stars will undergo binary interaction, sometimes leading to mergers. And so you can ask yourself the question, is Betelgeuse really that special? Is Antares more special? Is any other red supergiant more special than Betelgeuse? So just to finish, how could we go about answering this question? Well, I would suggest not by studying Betelgeuse harder, although that's interesting in its own right, but by statistical studies of samples of other red supergiants. And of course, we may not have the same data for those, but for instance, light curve studies, even if they're time limited or sparse, if you look at large samples of hundreds of red supergiants in local group galaxies, for instance, the Magellanic Clouds, M33 and M31, then you do get the statistics, and that's what we're looking for. Similarly, you could look at the nitrogen abundances in those red supergiants and rotation rates if you can measure them directly. So what can we say about what is typical for nitrogen content and rotation? Radio velocities, spectral energy distributions, any sign of companions? Or maybe can we infer past companions? 3D space motion studies, and also the question whether these stars may have been rejuvenated. For instance, if they must be older than they look like. This can point at mergers too. And of course, comparison with interferometric size determinations for nearby examples, their positions on the sprung ratio diagram, and direct mass estimates from seismology. And that will also indicate whether the star has evolved as a single star or perhaps as a result of a merger. But very importantly, we have to account for biases. Human beings tend to look for distinctive features and not the common. Thank you very much, and enjoy the rest of the workshop.
Okay. So I hope you could hear well the suggestions that Jacob van Loon sent to us. And with 8 minutes before in advance with respect to the previous timeline, I ask Alexei Bobrikh to start his presentation with a short presentation of himself as well.
Thank you so much, Constantino. It's a great pleasure to be here, and I'm going to be talking about the modeling of the formation history of Betelgeuse. And interesting enough, the things I'm going to mention is going to somehow continue the theme that Jacob van Loon's talk has started. So, well, I'll start with the key points straight away. So the 3 ideas I want to convey is that Betelgeuse likely was a binary star in the past. Even though it looks like a single star, it likely was a binary. Secondly, this phenomenon is not rare, and I'm going to try to convey you this idea later. And thirdly, Betelgeuse as a red supergiant is not a typical red supergiant for exactly this reason. And the things I'm going to be talking about are based on 2 papers, one by Manos Chatzopoulos from last year, and another one which is by myself and other people, which is about to be submitted literally this week or maybe next week. So Betelgeuse on the sky, very familiar, Orion constellation. We see it here. It is a red supergiant. It's a massive star, 20 solar masses. It's very large, about 5 AU in size, about 1,000 solar radii in size, and it's apparently single. But as we have just heard, it's also unusual in its features. So first of all, it exhibits rapid rotation. So Betelgeuse, if you look at Betelgeuse and look at its rotation velocity, we find that it's about 5 kilometers per second, which is really very large for red supergiants. As we know, the stars may be born critically rotating, but as they become red supergiants, they expand, and because of the angular momentum conservation, the momentum of inertia increases and their rotation rate decreases. So for even critically rotating stars, when they become red supergiants, they cannot spin as fast as Betelgeuse does. So it spins approximately 10 times faster than any star would be able to do if it were even critically rotating at the start. On top of that, as Jacob mentioned, we also have quite large nitrogen abundances in the atmosphere of Betelgeuse. And these are also a sign of strong rotation in giants. And even astroseismic signatures seem to indicate that there is something going on in its core, which indicates that it probably maybe was a binary, but I'm going to come back to that later. We also have heard that Betelgeuse is also a runaway star. In other words, it's moving too fast. So it's moving with a velocity of larger than 30 kilometers per second relative to the local standard of rest, which is a definition of runaway stars. It is located far away from star-forming regions. It likely can be traced back to the Orion LB1 stellar association. It has a bow shock, which is a typical signature of runaway stars, which have left their host locations and are traveling somewhere far away from the host, from the birth locations. And the thing is that Betelgeuse, again, both is a rapidly spinning star, it's a red supergiant, and it's a runaway star. And I claim that these two properties can be very naturally explained through this following scenario. Specifically, we can think about how do massive stars live. So massive stars are typically born in clusters. And we also know that about 20% of massive stars are found outside of clusters. And that happens so because massive stars initially sink down to the center of the clusters, and then they scatter off each other dynamically through dynamical encounters, and then some of them leave the cluster and end up outside of the cluster. Observations tell us that about 5 to 10% of massive stars, massive O and B type stars, are runaway stars. I remind you that runaway stars have velocities of larger than 30 kilometers per second, and they are traveling away from the cluster. So we observe many main sequence stars which are away from the cluster. And then furthermore, we also know observationally that about 70% of all the runaway stars are actually binary stars. So we know that about 10% of stars are runaway, and almost all of them, or 70% of them, are binary stars. Therefore, we expect that when the more massive of the massive stars evolves and becomes a giant, it will start potentially to interact with the companion. The observations don't tell us what happens after, and that's exactly the subject of our study. Specifically, we have tried to model a population of exactly these sequences of events. We have reproduced the observations of the massive runaway stars in the galaxy, and also have predicted what happens later to them. To do that, we have created a population of all the stellar clusters in the Milky Way galaxy. We have used the Monte Carlo generator to model the collisions of stars in the center of this cluster. We have used the few body code to model how exactly these collisions happen and what the products come out of that. Then we have integrated the trajectories of massive stars ejected from the cluster in the galaxy. And we have used the custom binary evolution code to model what happens later after this ejection. And with all this, we have created a mock catalog of all the runaway red supergiants which can be seen from the solar location. And we have compared it to the real catalog of red supergiants seen from the solar location, which was assembled with the help of Gaia EDR3 and also SIMBAT catalog. And put shortly, the key plot or the key result from this study is as follows. So here is a distribution of the binary semi-major axis of the massive stars or massive binaries which are ejected from clusters. And in the orange bars, we see the distribution of the stars which have been ejected, and in the gray bars in the histogram, we see the stars which have been left inside clusters. And on the x-axis, the range goes from 10 solar radii to about 10,000 solar radii. We see that the stars, when they are ejected from the star clusters, have typically separations which peak between about 100 and about 1,000 solar radii. That happens to be also pretty close to the maximum radii of red supergiants when they evolve, when the main sequence stars evolve and become red supergiants. And the thing is that when a star evolves and fills this Roche lobe, it starts to interact with the companion. That's inevitable. And also, when the interaction happens with the companion, the stars typically merge, and the binary in which the stars merge contains quite a lot of angular momentum. So the merging stars, 1 and 2, they spin each other up, and so as a result, we get a rapidly spinning remnant. This is at least a result of the 3D simulation, which has been done by Manos Chizopoulos recently. So here, a merger of a red supergiant and a companion star was done with a 3-dimensional hydrodynamics code. And then the result of that was mapped into stellar evolution code called MESA. And then it was concluded that the appearance of the merger remnant of such a star, of such two stars, can look like a red supergiant, can look exactly like Betelgeuse we see today. And on top of that, it's also rapidly spinning. So I'll bring back this scenario. So essentially what we have done is we have completed this sequence of well, observable data about what we see. And the key point from then from the study on this plot is that we find that because of the distribution of separations in these binaries, 80% of them interact when the primary is becoming a red supergiant, and as a result, 1 in 10 runaway red supergiants are both rapidly spinning and runaway. So in other words, if we look at all the runaway red supergiants, then among them, about 1 in 10 conservatively is going to be rapidly spinning like Betelgeuse. In this sense, Betelgeuse is not rare. Finally, just to summarize, we have been able to explain both the velocity, the spin, and the observational statistics of Betelgeuse. And this observation supports the standard model of mergers of red supergiants. And also as a side product of our simulation, we've also been able to explain the statistics of observed O and B type stars and also runaway BE type stars. As a final slide, I'll bring back the key points which I have started with. I hope I have convinced you that Betelgeuse was very likely a binary before in its past. This binary scenario is not rare. It's about 1 in 10 stars like Betelgeuse are rapidly spinning. And it's also not a typical red supergiant. In other words, the fact that it's just recently emerged, and by the way, it actually emerged only 100,000 years ago, might quite likely explain some of the anomalous features we observe in it today. Thank you so much.
Thank you, Alexei, for this presentation. And let's move to the next speaker, leaving the possibility to make questions at the end, but I see that the time is becoming short. So if there is some question, please use the chat to the presenter directly. Okay, so next speaker, according to the program and to the timing, is Sandeep George.
Yeah, okay. So I hope everyone can hear me. All right,
Yes,
so what I'm going to talk about today.
Okay, I am unmuting some people by my click just because I have learned how to do. But usually if you leave the microphone open, there are sounds. That's why. Go ahead, please, Sandeep.
Yeah. Okay, so so today I'm going to be talking about the nonlinear dynamics of Betelgeuse in some sense, and try and answer the question of whether Betelgeuse underwent a critical transition. Because this is going to be slightly scattered, it's important to start at the beginning, and I hope this is the beginning, which is at the end of 2019, Betelgeuse underwent a sudden and unprecedented dimming event, and there were many reasons that people said that this could have happened, and the causes could be suggested were dust, it could be convection based, it could be a pulsation, of combinations of all of these and all of that. Now, one thing that we do know is that there was no warning apparent from the previous observations that this thing was going to happen. And yeah, so with that introduction, let me just quickly switch to something else. And that is the idea of sudden transitions in dynamical systems. So in dynamical systems, we know that the system response can actually change quite suddenly. And in many of these cases, you do not have a warning from the mean system response. By looking at what the system behaved before, and at least the mean of that, it doesn't really tell you whether there's going to be a change in the state in the present or in the future, right? And broadly, in dynamical systems, we can classify these sudden changes into 3 types. You can have some kind of noise-induced tipping, which is like when the noise in the system contributes to a change in state. You can have a rate-induced tipping when the change in parameters, the quick change in parameters of the system causes some kind of dipping. And the last one is what we are interested in, which is the bifurcation-induced dipping. There's a nice review that I've put in the bottom of the slide if you want to read up more about this. Now, specifically for bifurcation-induced tipping or B-tipping, there's a phenomena that's observed called as critical slowing down. That is, close to certain kind of bifurcations, the system experiences an increase in the system memory and an increase in the system variance. Okay, and I will explain the next slide how this happens. But essentially, these are the two features that we find before this particular kind of transition, which is called the p-tipping. And these can be these. So yeah, so if we look at something, so if you want to measure the increase in the memory, we can look at the increase in the autocorrelation at lag 1, or you can look at the recurrence time of the time series when it comes back, and so on. And the variance can be looked at in the standard deviation or the variance. And I'll quickly try and explain how this happens. So I'm not sure you can see my cursor, but if not, the blue ball is what I want to look at first. So the blue ball is in a deep potential. So in a deep potential, what happens is that the ball is constrained to move within a certain amount of, it's constrained to move in a smaller area, right? So what this implies is that the variability of the time series, right, which you can see in the blue boxes over here, the variability of the time series reduces or is less, right? And the autocorrelation is also less because again it moves sort of within this potential. Now on the other hand, in the red case, when the system is in a shallow potential, the system undergoes something. The variance can actually increase. The variance it has larger area to move through, so the variance increases. And because this is moving slowly through this potential, the memory of the system also increases against articulation and lag 1, which you see in the red boxes. Right? Now, what we're saying is that when a system undergoes a critical transition, it moves from something like a blue case to the red case, and then eventually it tips into the second potential well, right? And this is not particularly, when can you expect this kind of critical slowing down, right? And so the case I talked about before is one specific kind of, it's called a saddle node bifurcation. But the same phenomena can be expected in a large number of cases when there's a Hopf bifurcation. That is when you have a sudden periodicity, a new periodicity is born in a system, you expect critical slowing down. In a period doubling bifurcation, that is when you have some kind of half harmonics coming in, like you have a main periodicity, you have something coming at, suppose you have a main periodicity at F, if a periodicity is born at F by 2, you would expect critical slowing down, right? And this is, and even a bunch of other, but these are the things that are most commonly studied. So now I think let me switch back to, no, actually, let me quickly make a case for early warning signals in general by talking about how much early warning signals have been seen before various critical phenomena across fields. And this is a number of publications that have been across 2 decades. And it really started booming at least from the 2010s when people started recognizing that this might be a feature before many kinds of transitions. Okay, so now I come to the second motivation, which is dynamical system theory in stellar variability. Now, it's not that dynamical system theory and stellar variability have been quite separate. In fact, stellar variability has been studied from the perspective of dynamical systems theory quite extensively, all the way from the 70s. There have been models which have been tried, which model stellar pulsations. We find very exotic phenomena that are normally seen in dynamical systems in observations of stars, things like period doubling, things like strange non-chaos, and things like that, and a whole bunch of things. So this gives us an additional motivation. We know that pulsation dynamics of variable stars is governed or seems to be well explained using dynamical systems. And we also know that sudden transitions in dynamical systems is often preceded by something called as early warning signals and critical slowing down. So this is what motivated us to go and look into the light curve of Betelgeuse and examine it for whether there were any trends in things like the autocorrelation and the variance. And our results seem to suggest that there was. And this is the light curve data from, well, the one in green is the one from about 1990 to 2019. And we see that so if you see the autocorrelation at lag 1, the determinism and the laminarity, all three are measures of the system memory. And all three of them seem to increase leading up to the dimming event. And even the variability of the system also seems to increase leading up to the dimming event. And if you look at the how significant we find that all quantifiers showed significant increases prior to the dimming. Um, okay, so with that, I think I'm more or less done. But let me quickly talk about the implications of what this means in Betelgeuse. The main implication is that the dimming was of a dynamical origin, which means that Betelgeuse probably underwent a change in the system state, right? And because we understand that nonlinear dynamics is the way to explain pulsations of variable stars, it could be that this change happened in the pulsation dynamics, and that's where at least I would probably. Um, and the important part to look at is probably the data since the dimming to try and look at which aspect is changing. Is it that the periodicity changing? Is it that the system itself has become unstable? Those kind of questions need to be addressed with the data from. Yeah, okay. So I think that's it. And because it's to an astronomy audience, I also want to talk like for 10 seconds about this is again from our recent review on early warning signals. Across fields, we find that early warning signals are prevalent, have been used to determine critical transitions in a whole bunch of fields, including ecology, medicine, psychology, where I currently work now, and so on. But the one thing that's missing is, of course, astronomy. And we know that there are many transitions in astronomy which are sudden. We also know that many of them have nonlinear dynamics leading up to it. So it would be nice if, like, maybe in a few years' time, one of this pie chart also has a slice from that says astronomy. And I'd like to thank my collaborators who made this work. And yeah, that's the end.
Thank you, Sandeep. And always I encourage you to use the chat for the question and answers. Eventually, at the end, we will have some time because there is 10 minutes extra, but as Andrea Dupri said, we will be full of Betelgeuse at the end. It's the time of Graham to take the word and the screen. Okay.
Okay, can you hear me?
Yes.
Yes.
You can, thank you. Okay, let's play it again. So first of all, good morning from Boulder, Colorado. I'd like to thank the session chair for inviting me to give this talk, and also like to thank the previous speakers for help setting some of the context for what we're talking about today. So today I'm just going to present two results, empirical results about Betelgeuse. The first is about the circumstellar envelope and how it behaved during the Great Dimming, and these observations were made with NASA SOFIA. And second, I'm going to just present some highlights on photometry from the ground, which looked at how the temperature of the star changed during the Great Dimming. So why have we been studying the circumstellar envelopes of red giants? For me, at least, mass loss is really key. These red supergiants lose a lot of mass, and we don't know how. So this is a basic physics problem. We don't have a standard model where you put in the mass, temperature, gravity, metallicity, rotation rate, and age, and out pops mass loss rate. So this is a really big problem, especially if you're interested in how stars evolve and their ultimate fate. For example, if you're calculating what a red supergiant is doing, like Betelgeuse, its evolution, theoretical evolution, the uncertainties in the mass loss rate are sometimes over an order of magnitude. So this is really big. So Betelgeuse could, for example, remain a red supergiant, or it could evolve to the blue. So not having a good handle on the mass loss rate is really key. And also having a good inventory of the material around a red supergiant when it becomes a supernova is quite important in interpreting the early timeline curves. So how do we pin down the physics? One way is to try and quantify physically what are the physical environments. So the physical properties we're interested in are the gas density, the temperature, ionization of all the elements, And then dynamically, we're interested in the turbulence and wind speed. So these studies are ongoing. And of course, when we're worried about what happened during the Great Dimming, we're really comparing observations obtained at this time, this epoch, with previous observations. Okay. So in this figure on the right-hand side, the SOFIA is really interested in this spatial region. You can see this is a dust image. You can see a quasi ring, which had long been known from interferometry, and this is an image from the VLT. And that's the silicate dust. And also we're interested in the gas component, which is not seen here. And that gas exists in the outside and also in the interior cutout, which is just a cutout to reveal an inner image from the VLT. So this is the spatial region that SOFIA is going to be looking at. So SOFIA is the latest generation of airborne observatories. It's a NASA German DLR joint observatory, 2.5 meter telescope, which is quite respectable. And it's on board a modified Boeing 747, which in my opinion is my favorite plane. It's quite remarkable to actually observe when you have a huge, you can see the top figure there, there's a huge hole in the side of the plane, and yet you're pointing the telescope with stability of a couple of arc seconds. It's quite amazing. And so when you're flying and they open the door at about 37,000 feet, you can't tell the door's open. There's no shaking or vibration. It's absolutely remarkable. And just below, for those who haven't seen a picture inside, that's the image looking towards the telescope at the back, and you have your mission director. And right in front of those heads that's the science team with their monitors, and on the left, it's the telescope operators. So that's pretty much what it looks like inside the observatory. Now we're using SOFIA in the infrared because the diagnostics of the gas around the supergiant are in the range of 200 to 2000 Kelvin. And the diagnostic lines, which we're using, they're emitted in the mid and the far infrared. And you can't do that from the ground because there's a lot of water vapor in the Earth's atmosphere. And so you need to fly, even at 39,000 feet, you're only above 99.8% of the water vapor. And that last 0.2% is actually quite a bit of a problem for us too. So that's why we're flying in a flying observatory. And of course, right now, there are no base observatories where above the Earth's atmosphere that can be dialed in to do high resolution spectroscopy. So we do need this capability. Getting time during the Great Dimming, probably every observatory had requests to observe, like Chandra, the VLA, and luckily the director of SOFIA at the time, Hal York, was very enthusiastic, and he sort of gave us the green light for as much as we could do. So I'm going to talk about two different instruments. One was XSEES, which is a spectrograph, it's a shell spectrograph, a resolution of 50,000, and then Upgrade, which is a heterodyne spectrometer, the resolution of 1,000,000. So these are the instruments we used. So this is the result we found from the XSEES, and let me explain this. We had on the left, that's the ionized, singly ionized iron, and this is a very strong emission line, as you can see by the flux scale. And we had two previous observations from different programs. One was in March 2015, one in 2017, and then Curtis DeWitt was excellent in getting observations on February 15th, 2020, which is just after the minimum. And if we look at the line profile, you can see the strong gaseous emission, and on a continuum, which is the silicate dust we saw in that previous figure. So this is a non-flux spectrograph, so we're only looking at the flux ratio of the line to the continuum. And that big dip just to the right is a horribly strong water feature, even at those altitudes. But the main takeaway point from this figure is if you look at the line width and the line centroids, they are within a kilometer per second of each other. And given that this is a spectrograph with slightly different settings on different days and different years, the fluxes are almost consistent with being constant. One of the little details is the blue seems a little stronger in this line. But if we move to the right-hand figure, this is a 9 of neutral sulfur. We only have one previous observation. And you can see there that the red and the blue curves pretty much for where you can trust the, you had another water feature on the right, are pretty constant in width and in central velocity and maybe flux. So the takeaway point from these observations, which occur in that gaseous envelope arcsecond out from the star is nothing much changed. Maybe there's a little increase in flux, but maybe not. So we move to the upgrade observations. Unfortunately, we didn't have any prior observations with SOFIA, but there have been previous observations of oxygen. First observations were made with the predecessor to SOFIA, the Kuiper Airborne Observatory, and they're the observations made in the early 90s. So the figure on the right just shows the date and the V magnitude at the time of the observation. In sort of towards the middle, you can see those LW and PAX. They are from the ISO and Herschel satellites. So these are above the Earth's atmosphere, and rather a curse and a blessing. The V magnitude of those observations was almost identical. And on the right-hand side, you can see that the observations with SOFIA were just after the minimum coming out. So we have those observations. So what was particularly interesting about oxygen is back in the 90s with the Kuiper, Haas et al. Noticed that the oxygen flux followed the V magnitude. And so this may happen, for example, if you change the photospheric radiation field, the radiation pressure on the dust changes, and that changes the dust gas heating of the gas, heats the gas up, and you get more oxygen emission. So that was like an idea or a hypothesis. And we were very interested in trying that because the V magnitude had decreased so much, or the V brightness had decreased so much. We were hoping to see a very profound effect on the oxygen flux if this was true. So this is my Confusogram. On the right-hand side, you have all the observations, fluxes. So this is an oxygen flux on the vertical scale and date on the horizontal. And you see in the early 90s, you have 3 fluxes from Kuiper. You have one which follows the red lines. Don't worry about the red lines. They're basically a tracer of the V magnitude. So it gives us a relative idea. And you can see that the FIFI and the CGS observations are much below the curve. And this is what was Haas et al. Was interested in. And if you go down to the bottom panel, you can see the space observatory fluxes are all roughly constant. And in fact, we have the upgrade flux at the very end is actually rather similar. And yet the red curve, which traces the V magnitude, is much, much lower. So it sort of generally supports the idea in circumstellar envelope that really nothing much was happening in the gas. But certainly something very weird happened in the 90s with the CGS and FIFI observations. To have a drop of flux of over a factor of 4 in a year and then a recovery is physically on the scales of arc seconds. That's really hard to imagine. But the takeaway story is the SOFIA oxygen marked flux doesn't supply any idea that the great dimming had any effect. Now, is that surprising? It's actually a null result. The dynamical timescales of these large envelopes is quite large. Out of the dust radius, it's 50 years. Halfway in, it's 25 years, 10 years, 5 years. So it's no surprise that the general dynamics didn't change on the timescale of a dipping of 1 year. The only timescale that can lead to very rapid changes is called the light timescale. And that may have something to do with the FIFI observation in 1993, or maybe not. Magnetic field timescales are also quite long for these. So the SOFIA observations show that the extended circumstellar envelope didn't seem to change much, and the dust continuum also didn't change much. So now we move on to the second line of evidence. And now this is ground-based photometry. So this is reporting on work by Ed Guinan and his collaborators. And this is, I introduced this technique, and it turns out to be absolutely crucial for the future interpretation of what happened. This is basically a free filter photometry system designed to be used on 20 centimeter class telescopes. You have 3 bands in titanium. And so titanium oxide is a molecule whose formation is extremely sensitive to gas temperature. So it's sensitive to the effective temperature of the star. And basically you have 3 filters, and you see on the right some simulations from Mark's models. Filter A, and the width of the filter is given by the horizontal bar under the letter. Filter A is a ground state, very strong absorption band, and you can see that strong feature. And just on the shoulder there, adjacent, you have a pseudo continuum band of B. So the ratio of those two essentially gives you an idea of how much cool material there is in the photosphere of the star. The one up the C band there is to give a small correction, which for Betelgeuse is important. That's also a pseudo continuum. So the way we can derive effective temperatures of stars is basically to measure these three bands, magnitudes, and take physically a flux ratio of A to B. And you calibrate this on stars with known effective temperatures. Okay. So what are the advantages? Well, obviously, if it's a flux ratio, it's insensitive to temperature. Insensitive to the distance to the star. So you don't have to worry about that. But more importantly for us, the ratio turns out to be insensitive to dust. So if you're looking at a star, there could be an interstellar dust cloud. It might have a circumstellar envelope with dust in it, or it could have both. And because dust opacity changes weakly as a function of wavelength, the wing photometry is at two adjacent wavelengths. It doesn't care too much. So whatever we see or measure with this technique doesn't tell us about the dust, and it doesn't depend on the dust. So just to reiterate that, because it tells us nothing about the dust, we can't make any comments at this point. The magnitudes themselves will tell you about attenuation by dust. So now we can apply this to, rather than a group of stars, we can apply to one star. So this is this figure shows a snapshot of 4 years of photometry obtained by Richard Wassertonic and Ed Guinan at Villanova. There's over 24 years of this photometry. This way here, you can see what's going on. And just before we start interpreting this, we have to remember these are spatially unresolved observations. So this is a mean value of the temperature. But I think you can see quite clearly here, the gold symbols, which are the effective temperature, 7-day bins, they follow the V magnitude. The V magnitude are the green dots on below, and the C magnitudes, which we don't need to talk about here, are the blue dots. And you can see there's like a gentle slope in 2017, a little scoop in 2017, a bit of a wiggle, 2018, and 2019, you see quite a distinctive drop in temperature. And then in 2019, we see the great dimming. So this is quite interesting. The temperature goes down. Okay, so just sort of step back. The reason the V magnitude and the effective temperature follow each other is that the V band also contains weaker titanium oxide bands. So since these are based on cooling and titanium formation, the temperature and the V magnitude are going to be tightly correlated. That explains the depth. So from September 2019, we get a temperature of 3,650, which is a typical value given cited for Betelgeuse. And you can see it continues to decline and fall down to at least below 3,520 Kelvin. Now that's quite a big drop, but it's actually not enough drop. If that were a single star at that temperature, the V magnitude would not have dropped enough to support what was observed during the great dimming. Now you'll notice there's a gray symbol.
3 minutes to go.
Okay, thank you. And you can see that's the measurement made in the V band by the shape of TIO bands by the Vest and Massey, and it's a different value. So how can we reconcile these different temperatures obtained at the same time? And basically, the idea is you have a multi-component photosphere, and that idea is suggested by, of course, this VLT ESO press release image that we had at the time. And if you have a cool dark patch at around 3,200 and a hot spot, what happens? If you look in the visible, you see the hot patch because the cool patch isn't emitting as much radiation. So if you're looking in that region, you will see a brighter temperature. It's biased towards the hotter material. But the cooler material also then forms an average with the TIO. And so this kind of simple model with no dust, no frills, can reproduce the VESC optical temperature, the TIO temperature, and the V magnitude. So this model is supported by Dewar Medina, who also came to this conclusion, I believe, before us, using submillimeter observations, which are also independent of dust. And interestingly, the recent Nature paper Montague seemed to also agree with this thing. How many more minutes do I have, Costantino? Oh, he's gone. Okay, I'm going to skip this slide. I'm going to leave this for Ed Guinan. Just to point out, this is incredible radial velocity correlation, radial velocity in green and V magnitude in blue. And you can see over the last 4 epochs, the amplitude has increased, and the correlation is very strong. And that tends to suggest that the cooling and the radial velocity are correlated, and maybe some form of pulsation is actually the underlying cooling mechanism. So just a few wrap-up points. SOFIA results showed that the extended region and the 25 micron dust didn't change during great dimming. We know, irrespective of what dust was happening on the star, the photospheric temperature did decrease through to the minimum gradually. A simple model can be constructed, which reproduces the V magnitudes and different T effectives. Don't need any dust because we know dust is around, so it may already be present. The photospheric radial velocity correlates very strongly with T effective, so suggesting a dynamical origin in the cooling. And finally, thank you very much for listening and spending your time with me. And now all we have to do is put all the evidence together so we don't leave any pieces out. Thank you very much.
Thank you, Graham, for this vast presentation. Among the things I wanted to say before and I forgot is that this meeting actually is during the following minimum of Betelgeuse. And as we have seen also from the data presented by Ottmar Nickel, the minimum is ongoing and probably is end already. Okay, I would invite Meredith. She already appeared for starting to share her screen. I know that we are starting to be a bit tired for this long marathon that is going to be realized on Betelgeuse. Okay.
Okay, can everybody see my full screen and hear me?
Yes.
Yes, okay. So I'm gonna try to condense a 30-page paper into about a 25-minute talk here. So the title of the paper is Standing on the Shoulders of Giants, and the primary result coming out of this was basically the discovery of new mass and disk estimates for this star from what I call multi-time scale evolutionary analysis, and also some rigorous observational analysis in Fourier domain as well. So I'm currently based at Space Telescope, but I will be joining you in the EU within the next year, most likely. So as we all know, in late 2019, Betelgeuse underwent this unprecedented brightness drop, and everybody's favorite word was unprecedented, and we all talked about how this was very abnormal. And shown here is sort of a depiction of that. So we have the visual image of Betelgeuse clearly being obscured by something, its brightness being lowered primarily in the lower right-hand quadrant, and then underneath a light curve that was generated along with the press release for this paper, showing sort of just for shock value, sort of how dim this star actually got in terms of its V magnitude brightness, and then comparing that to previous kind of pulsations that we have seen, but noting that the amplitude of this one was clearly much more severe. So as every stellar evolutionist in the world got very excited and wanted to address this question as it emerged, there were many approaches that one could take in trying to sort of understand why it dimmed or understand what was going on and the physics surrounding it. And the method of approach that my group chose was to see if we can reproduce this behavior, the sudden dimming behavior, with a range of simulations. So these were hydrodynamical, astroseismic, and evolutionary simulations to understand why Betelgeuse became dim, but just as importantly, to also rule out potential causes for its dimming. But to understand why this particular dimming event was unusual, we have to first understand Betelgeuse's normal periodic variations to give us some idea of why exactly this was anomalous. So the first step to this is to consider longitudinal brightness measurements of Betelgeuse for as long as we have them. So this is the observational analysis component of this. And what I show here is this really beautiful light curve put together by my colleague Laszlo Molnar, who has also been referenced in other people's slides, demonstrating Betelgeuse's change in brightness over the last 100 years. So beginning from 1928 until 2020, we have composite observations largely from the American Association of Variable Star Observers, but then also including in red here some new photometry that was processed and contributed by my colleague using the SNEI instrument, so the Solar Mass Ejection Imager instrument. Betelgeuse is so bright that you can background subtract the sun from images of it. So that was a nice contribution to this light curve. But what is pretty obvious here is that this dip most recently in the beginning of 2020 appears to be much larger than any of the other brightness drops that we have in this composite data. So I would say actually this is quite unprecedented on the surface, right? It looks this way. It appears to be the dimmest that this star has been in nearly 100 years. So in answering the first question, if we just look at the observational analysis, look at the brightness spectrum, it appears that we are actually witnessing something genuinely anomalous. But we can take a closer and sort of more mathematical look at this by analyzing the potential pulsation frequencies and the periodicities in the Fourier domain. So from this new and archival photometry that we assemble, we find periodicities, and there's a subtlety here. Periodicity does not necessarily equal an intrinsic variation, right? It's just what we observe. The most dominant periodicities that we find are 416 days, so we call that a quasi-annual variation, 165 days, and then about 5.6 years. And so these are the ones that are sort of uncovered. They have the largest amplitude in the Fourier domain. But this doesn't actually help us in terms of determining the drivers of the physics, right? And determining the drivers of the different frequencies can help us in some cases probe the structure of the star. So what we want to know is whether this 416-day quasi-annual periodicity is what we call the fundamental mode. And by the fundamental mode, we mean the highest amplitude in Fourier space mode that is driven by acoustic pressure variations. So that's an astroseismic signature, right? And if we can classify that as the pressure mode variation, then this allows us to, it follows from that the 185-day periodicity is the first overtone of this in astroseismic terms. And the way that we can sort of prove or demonstrate that the 460-day periodicity is driven astroseismically is to determine whether it's driven by the kappa mechanism. And this is something that we can assess by running different kinds of simulations and actually examining the structure of the stellar model at the time that these pulsations are occurring and looking at what is going on in the outer convective envelope. So pulsational analysis is particularly powerful in the context of stellar evolution because constraints on mass and evolutionary stage, especially for very high mass stars, are often quite weak. And we have all these additional parameters to consider, like mass laws and things others have said. But what frequency analysis can do is help reduce a lot of these parameter degeneracies that emerge naturally when you're running stellar evolution calculations. So I've just summarized what our key periodicities are here, and then I will try to convince you that I've classified them correctly throughout the rest of the talk. Okay, so the key tool we use is MESA, the Modules for Experiments in Stellar Astrophysics. This is the most widely used stellar structure and evolution program in astronomy. It generates structural, evolutionary, and hydrodynamic models of stars. So that last class is something that people may not be aware of. But what I show on this slide in the left-hand panel is just an evolutionary track. So these are temporal-based models of a star's trajectory. And then in the lower left-hand panel, I'm showing some very short timescale hydrodynamic simulations that can also be generated with equations of motion rather than equations of structure with MESA as well. And then I'm also showing our slide that the MESA team always puts up, which shows all of the users all across the world. We are very proud of our large user base and then the members of the current development team. So MESA is 1/3 or 1/2 of the tools required for this. And then another equally important component is Gyre, which is a stellar oscillation program. So it actually solves the equations of oscillation directly to predict a body's response to perturbations. And these are linear adiabatic perturbations in our case. And then thus they generate a theoretical frequency spectrum. So this is then a theoretical output that we can compare directly to the observed frequency spectrum that we have obtained by looking at the longitudinal brightness deviations. And in this case, of course, the body that we are perturbing is a structural model of Betelgeuse, a high resolution structural model that is generated by MESA, generated with the evolutionary calculations. Step 2 is to build our best possible evolutionary model. And we have to just run a bunch of stellar tracks that end up being consistent with observations. And because the mass constraints on a star like this are quite weak, and the birth mass constraints are even weaker because we don't know what its past life was, right? We don't know if it was a binary. We can't know that a priori. So we just have to guess sort of at a configuration and then look at the models that end up being consistent with observations. So we consider a whole range of possibilities, everything from 10 to 25 solar masses as the birth mass. Of course, again, understanding that this is just one assumption of its possible history. And then we look at the red giant branch phase, which are quite, rigid and quite strict. So those are the pink region in vertical bars here. So that's quite constraining in and of itself. But something we need to be mindful of are also the theoretical parameter degeneracies and also the uncertainties intrinsic in our calculations. So these observational constraints for the temperature are obviously excellent and really tight. But we also need to consider what happens when we just change our ad hoc assumptions about convection and the other underlying physics in stellar models. And it turns out that we drastically eclipse the uncertainty provided here just by varying what we call the convective mixing length to within kind of literature reasonable values. So rather than just restricting ourselves to the observational constraints, we need to actually expand our interpretation of consistency that account for these ad hoc modeling choices. So that ends up being the region in blue. So this is the whole space that we actually consider. So what do we learn from performing the evolutionary analysis once we have this set of consistent models? Key insights. So statistically, we find that it's most likely Betelgeuse is in its core helium burning phase, which actually places it at a little bit younger of an evolutionary stage than what was thought previously. So we actually find that it's sort of in the beginning of its core helium burning phase rather than towards the end. And that's going to revise its lifetime estimates quite a lot. And how we determine this is using a Monte Carlo simulation interpolated over a grid of tracks spanning mass and possible metallicities, again from observational constraints, and then restricting to radii between these values that we find we need to have in order to be consistent with the seismology, and I'll get to that next. And then in the figures here, I'm just showing a few of the iterations from those simulations, courtesy of Mike Ireland, who's an interferometrist and contributor to this paper. We find, as others have said in the session, that it's not possible to reproduce Betelgeuse's present-day surface rotation rate with a single star evolutionary scenario. So this supports, that there must have been a past merger or binary interaction. It's definitely the case that some source of spin-up is required to get Betelgeuse to be rotating at the rate that it's observed, which I think is about 5 kilometers per second or so. And the likelihood of a previous binary interaction is also supported by kinematic analysis and its current proper motion. So it's in a weird place, it's moving in a weird direction. These are things that others have said before as well. Part 3 of this is incorporating the astroseismology. So now that we've restricted the domain of viable models to this region I've circled here in the HR diagram, we're going to use this gyre tool to perform linear seismic analysis on observationally consistent tracks. And all of the observationally consistent tracks are those that intersect the uncertainty adjusted effective temperature constraints. When we do that, we can determine which models are seismically compatible in addition to what we call classically compatible with the observations. So here I show a period versus age diagram where I have organized the models by mass according to the color of the marker. And then the shape of the marker represents some variations to these convective assumptions that I don't need to spend too much time on. And the blue horizontal region represents what we later determine to be the fundamental mode. So I'll just call it that for ease of communication. The fundamental mode and then the uncertainty on that. So we have this periodicity of 416 days plus or minus 24 days. That's this region here. And then of all the masses, the predictions from Gyre already restrict the mass domain to this really small region here. So we're looking at about 17 to 21 solar masses or so for its present day mass, just according to what Gyre tells us about the frequency spectrum, and then comparing that to the observed frequency spectrum. And we conduct this under several different assumptions for consistency, but I'll only spend time explaining one example. And then similarly, we use the same seismic constraints to obtain constraints on Betelgeuse's physical radius. And it turns out that the radial constraints we get by applying this technique are much tighter, much more precise than the traditional interferometry plus parallax method that would be applied observationally. So I'll focus on the upper panel here, which shows the radius, again, as a function of period for the where the theoretical calculations are in the star markers, and then the observed constraints are in the green vertical bars now. And the range of radial values permitted by this analysis are between about 650 and 800. And whereas from literature observations compiled that we looked at when we were writing this paper, there were estimates ranging from 600 solar radii to 1300 solar radii. So we're getting a much tighter range of allowed values using this technique. And then we also similarly get some constraints on the final mass and the birth mass, but given that we don't know what its evolutionary trajectory was up until present day, you can take those with more of a grain of salt. So the results from the classical and seismic analysis, our general finding on the initial mass of Betelgeuse, we don't do much better than other modeling efforts, other papers. We're literature consistent. We're not that much more precise. About 18 to 24 solar masses, that's fine. But our models permit only this very small range for the physical radius, which is a 3 sigma band of about 150 solar radii. And this range is considerably smaller than predictions for the physical radius provided by the traditional observational method of interferometry plus parallax. And I'll just go over a little bit how the inversion of the distance inference actually works. So typically we would combine the parallax, which is 1/d in this figure, with the apparent size or angular diameter to obtain a prediction of Betelgeuse's radius from direct measurements. But in our case, we already have a theoretical radius from our models, one that is very tightly constrained and must be permitted according to the seismology that we've computed. So now we have a theoretical radius from our models, the observed angular diameter still, and then we can invert this to obtain the parallax. So we actually call this our seismic parallax, and it was an unanticipated bonus of this analysis. So the precision modeled radius plus the measured angular diameter gives us a new completely independent means of estimating the distance to the star. So the revised distance for Betelgeuse comes from this seismic parallax that we've constructed, and I've just shown this figure up to put our measurement in context. So we have the distance versus the distance measurements, and then various groups and instruments and their predictions for the distance. And as you can see, ours is here. We set the gray region according to our uncertainties, and it's nearly the most precise thing there. And it actually very nicely bisects the last sort of 5-10 years of measurements and other like highly regarded results for this. So there was some discussion in the public science domain that we've moved Betelgeuse so much closer to us, and that's actually not true. We're perfectly consistent with literature values recently. It's just that our range is more precise and our centroid value is smaller than what others have found recently. Section 4 is the hydrodynamical simulations component. So we can reproduce some of Gyre's linear mode classifications with hydrodynamics, and we do this to produce self-consistent mode classifications. So from very short timescale hydro simulations, we can extract the cycle lengths as a secondary means of estimating the oscillation periods. And we should assume, we would hope that the cycle lengths give us the same periodicities as both what we observe and what Gyre computes. And then this is where we can really start looking at the driving physics of the different modes and whether those modes emerge or not. So what I show here is a figure from my colleague Xingqi Liang, who has also presented at this meeting, demonstrating the oscillation patterns of a few models with various different initial masses here. So what we can do with this information is also construct a synthetic period radius relation. So this provides additional evidence that it is Betelgeuse's shorter pulsation period mode that lies on the fundamental mode sequence, right? So we had this potential 6-year periodicity, but we don't see that in our simulations, right? And so we can actually kind of demonstrate that this long secondary period is not a part of the astroseismic analysis we're dealing with by constructing this synthetic period radius relation. So the red circles in this figure are Betelgeuse's 400 day periodicity and its 5.6 year periodicity. And then all of these little colored circles are simulations where we've extracted cycle lengths for stars of high mass. And then down here in gray are actual observed period radius relation values from lower mass oscillators like Cepheids and things like that. So we can already see that it's Betelgeuse's 416-day period rather than 5.6 year period that is falling on this sequence. So with hydrodynamic calculations, can we activate a mode that's consistent with the fundamental mode, the 416 day mode? And the answer is yes. And then the second, arguably more important question is, can we conclusively determine the driving physics of that mode? And the answer to that is also yes. And the way that we do that is by examining the structure of the envelope of the stellar model at critical phases in its pulsation cycle from the hydrodynamic simulations. So looking at the rising centroid, the dropping centroid, the troughs and the peaks, and then also analyzing structure at critical times, which we do here. So by examining the envelope structure at critical points in the pulsation cycle, we are actually able to sort of show that the free electron fraction and the opacity ratio, these are all doing what we would expect at those points in the pulsation cycle for the kappa mechanism. So because we have this very high resolution simulation with all of these quantities that we can explore directly, we can demonstrate what the driving physics is at these points of time. And we can show that for some of our simulations, this does emerge, and in some of the other pulsation modes do not emerge, right, which gives us some kind of insight here. So the physics here is a bit complicated, so I'll just say, yes, it's the kappa mechanism. This is clear from the electron fractions moving around and how the atmosphere behaves, how the convection envelope behaves at certain times. So the answer to question 2 is, can we conclusively determine the driving physics of the mode we're interested in? And the answer is yes. So the insights we gleaned from the hydrodynamic simulations, we're able to generate quasi-annual periodic variations using models that are consistent with the radii predicted by our evolutionary and seismic models. Our structural analysis is consistent with the kappa mechanism as the driver for the fundamental mode. There's no emergence of the 6 or 30-year periodicities in our hydrodynamic analysis, which suggests that neither is driven specifically by acoustic variations in the envelope. And then some stuff I'll just kind of gloss over here. We also have some preliminary results suggesting that nonlinear excitation timescale could be sensitive to mass. This could be another way to probe things. That's work in progress. So I'll just give my summary slide now. So key results from all of these 4 analyses methods. Models are consistent with the need for a spin-up event to cause present day rotation rate. The kappa mechanism does drive the 416-day period, which is the FM. This in turn allows us to classify all of the other pulsation modes. It is a double mode pulsator. It has an overtone period of 185 days. The 5.6 and 30-year variations are not caused by intrinsic variations. And I'll add an asterisk here. So at least they are not caused by ones that can be captured with 1D linear pulsation physics. Your mileage may vary if you use nonlinear models. Betelgeuse is less massive, smaller, and closer than we thought. Its current nuclear burning phase suggests it will not go supernova for at least 100,000 years, which is about an order of magnitude higher revision from previous estimates. And seismic parameters were the key to modeling this problem. The I was happy to get some mainstream, pop science coverage for this piece, and I will just leave the reference up here, and thank you for your attention.
Thank you, Meredith, for this incredible amount of informations extracted by your table, because in Latin, or probably also in Spanish, mesa means table.
Table, right, yes.
And well, I was asking to myself if the figure I read, 424 plus or minus 16 days, was a result of a bunch of simulations with slightly different entries, or was the intrinsic variation of this main pulsation period, as usually occurs in variable stars?
Yeah, so I think the word main is a little bit confusing, because the dominant period, if you look in Fourier space and you say what has the highest amplitude, that's going to be the LSP. But that's not something that we can reproduce with hydrodynamic or astroseismic simulations, because it's not actually driven astroseismically, right? So the acoustic pressure modes are just one type of cause for all kinds of periodicities. So the fact that this 5-6 year variability cycle did not emerge in any of our simulations just suggests that it's not an astroseismically driven period. So I think it's the LSP, but we're classifying that by ruling out other causes, not by demonstrating it. I think the 30-year variation is interesting too. So this could be something to do with rotation. And certainly I'm very interested in insights on that. But in our case, one of the reasons we couldn't actually explain the Great Dimming event after all of that effort was because our models only encompassed intrinsic variation scenarios. And it turns out that the dust cloud was not due to intrinsic variability.
Okay, I don't know if there is someone who wants to do questions. Because I have another one on this subject, and this MESA simulation can reproduce oscillations, or oscillations are such a statistical properties, I don't know how to say. So you can follow 1 year of simulation, or you have billions years simulations at once.
So the time scale matters a lot, right? So when we were probing this astroseismically, we're looking at intervals of 10 or 100 years. When we're probing this evolutionarily, we're looking at, millions of years to billions of years. So oscillations can occur on all different kinds of time scales. In the case of gyre, this was actually a static model that was perturbed. So we're looking at very local oscillations, and which kind of simulation or which time scale you use is going to uncover different physics, is what I would say to that. So can MESA do oscillations? Yes, if they are driven by evolutionary situations like thermally pulsating AGV stars, like those are natural evolutionary behaviors. And so MESA's perfectly adequate for probing that kind of thing. For these very short time scale oscillations, I think gyre is the tool that you want to use. And then, of course, hydrodynamic simulations, it depends what the resolution of your time scale is there too. So are you looking for such small oscillations that you need time-dependent convection? Well, that's sort of a separate problem, right? So in this case, I should say we were not using any kind of implementation of time-dependent convection for any of the stuff we're looking at. But perhaps if you did and you probed even smaller timescales, you might see some of these other periodicities emerging in the simulations.
I want to do the last provocation to the audience, is what Betelgeuse will do the next. As the same provocation is for our sun, what 25th cycle of solar spot will be? Or if we will fall in another Maunder minimum. we have many instruments to probe this problem. For example, the things that Sandeep presented to us. Can you find in your studies and simulations some statistical property in time series that is that has an astrophysical origin of variable star, obviously. And the answer to what we'll do the next, because we all think to that. We follow Betelgeuse from less than 1 century, or 1 century.5, as Edward will tell us in the next talk. Are we able to know what will be the next?
Next what? Are you talking about the sun or Betelgeuse?
Or the sun or the Betelgeuse, the intensity of the maximum, the intensity of the minimum.
Well, building predictive timelines for the future behavior of stars is the purview of stellar evolution, right? I mean, the thing that most people were interested in with our analysis was, dust cloud aside, when is Betelgeuse going to blow up? And we can't get an ultra precise estimate of that because we don't have ultra precise observational constraints. But when you incorporate the seismic constraints, it makes the problem a little bit better. All we can say for stars that are as poorly constrained as that is it's probably this order of magnitude or that order of magnitude. But our ability to be predictive about these things is largely a function of how good the observational constraints are and the period over which we have those observational constraints in the case of variable stars. So the ones where we have these long longitudinal photometry for I think somebody once wrote a paper looking at variations from the 1600s up until now. So when we have those time scales, I mean, that gives us a lot of extra information about the pulsation physics, and then that's something that we can at least match against when we run our simulations.
Okay, I see that Edward is more than ready to present.
Am I?
Talk. I put in the program some small gap, but since we can switch the video down, we can take our coffee during your talk, and we did in the past the past talk as well. So
I'm happy
please,
with that.
Go ahead. I wanted to read what you sent to me because well, I asked to send me a small presentation, but I forgot to present them, and actually. Well, I had it on my PC, but now it's gone away. So I will do an improvisation saying that, well, on 8th of December 2019, after 2 days of my observation of Betelgeuse after 2 months of clouds and rain here in Rome, Edward came out with an astronomical telegram saying that Betelgeuse was going to magnitude 1. So he announced to the world that Betelgeuse was doing that. So I immediately went to check his curriculum, and I understood that I was in front of a person who controlled Betelgeuse from a large part of the known history of this star. So please go ahead with your presentation now.
Thank you. Can you hear me?
Yes.
Okay, thank you. I wish I could control Betelgeuse. So you wanted me to do a kind of general talk, and I kind of mixed it in with new results. So twinkle, twinkle, bright red star, how we wonder what you are. We're still wondering. My collaborators are listed. Graham Harper gave a nice talk, and the other people are collaborators. They do observations. The last three people are students, undergraduate students, who are going over and back in history, vetting each of the observations on Betelgeuse and other red supergiants. It's a beautiful picture of Orion and Betelgeuse from Hawaii. It's just a beautiful, it was when I was 5 or 6 years old, that was the first constellation I recognized, like many people. And I was given a telescope at Christmas, and I looked at Betelgeuse and the Orion Nebula. You wanted me to cover this. I mean, this is the origin of Betelgeuse and Orion. Orion really goes back to Gilgamesh, Persia, and Middle East. And then it was taken over by Greek. So this is an early picture of Betelgeuse, although it is not Betelgeuse, but Orion. Gilgamesh was the great hunter. And there's Betelgeuse right there. The name is wrong. I mean, I was trying to push for properly naming it. It's Yad al-Jusa, it should be, because of dropping a little point it means the hand or the arm of al-Jusa, and just getting that one little dot wrong in Arabic and Persian, 2 dots instead of 1 dot, caused it to go from a Y to a B. So they're Betelgeuse. And so these I went and saw the original of this in Mashed. It's a 964 book. It's earlier, this is a later edition. I was checking to make sure that the magnitude was still 1, and it was. The more traditional view is Orion the Hunter and fighting the Bull of Heaven. And there's the one you usually see. This is from Flamsteed. An unusual one is I gave a talk in Africa a month ago at the East African Astronomical Society, and I found this different representation and story of Betelgeuse and Orion. Well, doesn't exist. So the story goes, the Pleiades over here are the children of the sky god. Aldebaran is their husband. He has several, 5 or 6 wives. And he's a hunter. He has to go out hunting. And what happens to him is that there's 3 zebras being watched very carefully by the lion. The lion is Betelgeuse. And he shoots his arrow and he misses them. So this is the Orion sword. This is the belt. And he's so embarrassed. He was afraid to retrieve the arrow or spear, that he so embarrassed and shamed that he still goes wandering the sky, afraid to go home because he didn't bring food to his wives. Maybe he should have less wives. The other one that comes into play is that how it's William Herschel. John Herschel was the discoverer in Western world, but there's some papers coming out that Betelgeuse was recognized, possibly recognized for oral traditions of Australian Aboriginals hundreds of years before Herschel. And here you see, I think it's blocked by me, by the picture here, them arguing what type of star it is, variable, supergiant, dust, pulsation, all that. This picture of it, it's a huge star. And here you see the solar system, and parts of it go out to Jupiter. The surface is nearly Jupiter. And then all these nebulosities and things go out to the edge of our solar system. You see it in the picture that was shown previously. Here's Orion, here's the belt. The belt, the sword. And there must have been some sort of this is called Barnard's ring, a supernova explosion that possibly took place in there. Tracing back the origin, Graham and I tried this, it's just that there isn't precise enough distance and proper motions. It generally tracks back to the Orion nebula region, and this is where it is now. It's because of uncertainties in distance, things like that, you can't track it back as carefully, but it comes generally from in this direction. Maybe the explanation for its oddness is that it had a binary companion that supernovaed and ejected the star out in that direction. Who knows? There's many, many pictures. It's amazing, the technical world, the imaging that can be done. So here's a picture of the whole region by Corvella, Montegas, by Miguel. And that little dot in the center is blown up. And here you see now our classic pictures of taken by the VLA of a Betelgeuse showing the variations since January to March, showing the dimming. Here's some pictures of it goes back, I'll let it run, it goes back 50,000 years. And you see that many of these stars are changing because they're near, here's Aldebaran. But you'll notice that this picture in here, these stars remained fixed in this unit of time. So it is a runaway star, as was suggested. Most of these stars, massive stars, have binaries, or they're in star systems. Betelgeuse is not, which leads its rotation and things like that lead to the conclusion that it was kicked out. It was of wherever it was formed, probably in the nebula. Properties of Betelgeuse. I didn't know what kind of audience this was going to be, and so this you had the brightest red supergiant. It may or may not be the nearest. Antares is pretty close too. RSG is the word for abbreviation for red supergiants. It typically is the 8th to 10th brightest star. It has these periods. Meredith found, and we saw it too, 186-day period, but basically these two periods are the dominant ones. Summary, the great dimming, I called the great fainting, and I was corrected. I thought it was kind of cool to call it that, and it went down to 1.6, the faintest that's ever been observed. It was 60% brightness decrease. From our TIO photometry, it was the coolest, so it had a spectral type of M4, it usually is M2. And it had the largest recorded radial velocity amplitude of 10 kilometers per second. Graham showed that. It is a supernova progenitor. When it does blow up, it's somewhere it's going to be V around -10, -10.5 or so. Joyce Meredith, Joyce could be your first name too. Meredith had a nice paper that she just went over in this conference. So what I did down here is what I revised. I put in her values to update these via the MESA code. The parallax is 222 from Graham Harper. That's actually a parallax, because it's been measured. The one that Meredith found is a theoretical distance. So that's from Harper et al. It's a giant star. I mean, it has convective cells. They've been actually seen. This is the solar convection. These are granules that are the size of France or Pennsylvania, if you say. And on Betelgeuse, they're about AU across. These last 5 minutes. These could last years. So this is what's driving the system. There might be pulsations in there in the center, but as the star expands out, it's going to encounter these giant convective cells and alter them. These have been imaged, kind of reconstructed from spectropolarimetry. There's pictures here, and I have to kill this picture because I can't see the side of the screen. And there's even from ALMA, there's even shows an asymmetry, indicating that some of these convective cells or pulsations actually, overshoot the mean surface of the star. This is Borman and Corvella. Corvella does a lot of work on this star. For those which I was expecting, this is the usual. This audience doesn't need this. It began as an 08 star or so, Betelgeuse, and went across here to become the red supergiant. In a more technical terms, this is an evolution track showing Betelgeuse at the very top here, along with Antares. Even a brighter star is VY Canis Majoris. So for more technical. This is the evolution of a 15 solar mass star, kind of similar to Betelgeuse, where it is around here, it's an A0 main supergiant, and then it becomes convective. And right now it's most likely in this stage, burning hydrogen into carbon and oxygen and so on right in here. It depends where it is in here. Meredith's model shows it early. If it's later, it actually will become supernova within about 5,000 or 6,000 years. But if it's in this stage, it's early stage of this, it could be 500. The top person, nice person, not nice, Emily the Vesquez, spent a lot of her life studying Betelgeuse and red supergiants, and she has this nice book out on astrophysics of red supergiants. So briefly, I'll go back to this. A very brief life and times is that here you go. It goes through the forms. An 08 or so star evolves to become a red supergiant and then blows up. About 1 out of 10 chance of blowing up, because there's some supergiants that fail to blow. Most likely Betelgeuse will become supernova. In any event, it's either a black hole or a neutron star. Most likely because of its higher mass, it's a black hole. I'll go back to that supernova part if there's time. So there's 180 some years of photometry. The Aboriginal people of Australia didn't write down any numbers, or they have oral tradition, so we can't use that. Going back to Sir John, the son of Sir William, who noticed it accidentally when he was visiting South Africa. Here's the AAVSO graph. It's semi-regular. The dominant periods were found by Keys, Carvella. Oh, sorry, that should be Keys in 2006, where again you find these two dominant periods, 388 and 5.6, and so on. And what I'm going to do here is I'm going to use the whole data set. This is nice. This is from Christopher Lloyd, who gave a paper at Constantino's previous meeting on Betelgeuse, which shows it nicely. I should have used Meredith's nicer graph because these are 10 day normals. And here you see the variations, and here you see the great dimming. I have to point out that in studying other red supergiants, that's not so great. VY Canis Majoris drops 2 magnitudes, 2.5 magnitudes during these events. Mu Ceph is even bigger. So compared to Betelgeuse, yes, it's the biggest one, a magnitude drop, but other red supergiants show even larger dispersions. Here's a plot of all the data. This is where my students got involved, going back into the archives, collecting all this data. This is BAA, British Astronomical Society people, and this is mostly the, or almost entirely AAVSO. It's like 40,000 observations here. We had to vet things like this observation here not used because people have different observing schemes. So we had to go back and see, who were the best observers and who were not so good. Maybe we're having wine evening they were observing. So we did an analysis of these for the first time, the whole data set, 1837 to 2021. And these are the periods that you get. You get the 420 day. It's roughly, it varies between 385 and 430, but we'll call it 420, a big signal at 5.7. This is 19.9, and which I'm not sure where that comes from, and the 39 period shows up when you do the cleanest. These are all from Parenzo for a transform analysis, and here's a blow up of the shorter periods. And here you have Meredith's 1.85 day period right in there. A nice scheme is to see these change with time, and over the almost 200-year interval. This is a wavelet analysis, WWZ wavelet analysis, Foster in Parenzo. We use that to analyze the data. And here you see a 7.5, a 39-year period. That's pretty strong. Orange and dark colors are stronger. This is scale here. Blue's nothing. When you get into the greens, but the orange colors give you stronger, more I say robust periods. Down here you see the 400, the 2000. This is the 5-year period. I'll blow it up. Here we have just the bottom. This is enlarged. So here you see the 4.5 to 6.1 day period, and this is the 400-day period showing up. These are the two consistent periods. They're kind of always there, although they fade. There's not much data in here, so it's weak. Same thing is true here. And you have it going out to the present time. I'm going to blow that one up. So this gives you the Parenzo plot showing you a clearer picture. The 400-day period, the 5-year, 5.6, 5.7 year period. And notice these things that are happening here. There's a split here, which when periods split like this, it shows in stability. Nothing really happened in near the Great Dimming, which is out in here. We don't have enough data. If you collect this data 2 or 3 years after the Great Dimming, you might be able to see something for the wavelet analysis. Just for comparison, here's another red supergiant, even bigger than Betelgeuse. And here you see it has more complex period dynamics changes. Here you see generally a 5,500, 400, 8 year or so period, 54 that splits. And here you have the 870 day period. So this is like the 2000 day period in Betelgeuse, and this is like the 400 day. Notice it's twice. These periods are longer. It might be because of period is proportional to 1 over the density of the star, square root of the density of the star. This is indicating that mu Ceph could be, and probably is, larger, less dense than Betelgeuse. Have to be careful here because these are red supergiants. This was the surprising result because I've seen this data all along. I've had Joel Stibbons is the premier pioneer of photoelectric photometry. He invented it 1908 up to the 30s. And he has photoelectric photometry of Betelgeuse. And they took out the 400-day period. And here's a plot on, they used to plot this in this way on a 5.7-day scale. So this would be a phase of 0. On a modern day, this would be 1, but they plotted it in days. So here you see the minimum light, maximum light, and amplitude of 0.2 or so magnitudes. And down here is the radial velocity curves that were available. This is a bright star. People then could still do radial velocities of supergiants quite well, plus or minus 1/4 kilometer per second. And here you see what was kind of amazing to me is this radial velocity curve, and the two of them, one from Lick, one from Cape, which are similar. And you see a 2-kilometer excursion. Here it's expanding, or coming towards you, 2 kilometers, and here it's going away. What you notice in here is that this is very similar to a Cepheid variation. If you think of that, then the minimum, see it starts expanding rate. So now the maximum is going to expand, and here its maximum radius would be here. And that coincides with minimum light, just like similar to Cepheids. And here's the star at maximum infall or contraction rate. And then it will slow up, and right here it's 0. And it has reached radius of minimum, very close to what Cepheids do. So this is kind of amazing, and this is 70 years old. I went back and analyzed it, checked it out, and it works. And if you take the modern values of V magnitude, TIO, and effective relationship, this is cool, and this is going to be the hotter portions. So I question this. This looks to me like pulsation. And this is the long period, the mysterious long, that's why I call it the mystery of the nature of the long periods. Just checking my time. I started doing Betelgeuse, well, I don't count when I was 5, but in 1982 at Villanova University, we did it because it's in the city and we can observe bright stars. And that's why it was no astrophysical reason chosen, except that it's a variable star and it was easy to observe, relatively easy. And then this was done with strange filters. In fact, Andrea and I, the data was used in one of Andrea's papers in 1986. But since 1995, we switched over to a 10-inch or 25-centimeter telescope and moved it off campus to Richard's backyard. So all the observations you see here are going to be done with a 25-centimeter telescope. This is the V-band, so this is 25 years of data. Here's the, you see the 400-day period. You actually can see the 5 to 6 year period in here, going down in here. It shows up very strongly. This is the periodogram. This is the Fourier analysis using cleanest. You see the periods there, the 6 year, the 430. So as Graham discussed, this was a little telescope, but we were kind of clever about it. It had IR response. So we had titanium oxide filter on the titanium oxide band, one filter off and another one out where there's no line, very little lines that served as a bolometric magnitude test. But with this little telescope, we were able to do things that a larger telescope would be needed just by using filters and having a small telescope that was in Rick's backyard. I'm going to get to the great dimming. Now, in observing the star over 25 years, we were going to give up. You know, I always had in the back of my mind, you know, maybe it would blow up, you know, who knows? The chances were tiny, but I wanted to see it. So we were going to give up in 2019 because it was getting boring. We had enough data to do our analyses. And then this happened. It started to, usually it goes down to 1 magnitude. We were expecting it to happen on the 420-day period on February 15th. So it did happen then. And then this is when I sent the telegram out, that not knowing it was going to continue, but knowing it was fainter than it ever has been and coolest it has ever been. And this is when we started to send these telegrams out, alerting the community to maybe take observations of it. So this is the first season. Our very last point was in April 27th, 2020. It was nice doing this because it was a backyard telescope. COVID didn't bother us. You know, he was up there, I was at home. So we were able to do this. Betelgeuse dropped from, you know, from 9th to 25th. It lost its status. This telegram that was sent out, this telegram surprised me because it was elicited a lot of responses, and there were second and third telegrams were sent out, astronomers' telegrams. You could actually see it, you know, you look up at Orion in the end of December, January, and the shoulder, it looked odd. And because to the eye, you can easily see that it was much fainter than it normally was. So after this, there became a Betelgeuse Frenzy of sorts. Newspapers and all like, and even me was produced. It has its Twitter account and it has a bot which gave each day what Betelgeuse was doing. So getting back to what Graham talked about just quickly, we analyzed all the titanium oxide and the V-band data, and it's shown here. And it showed that as the dimming took place, it had an unprecedented drop in temperature, dropping to about 3,600 degrees or so, the mean temperature. And this is Graham's analysis. So what was going on, we would have accepted that. We probably would have, without seeing Miguel's features, you know, the images, we would have thought maybe the radius contracted, because it wasn't enough to explain the 1 magnitude drop. But when you see half of the star is dim, it was enough, because then you have we were getting the mean. So this part was producing less energy, and Graham modeled this and was able to determine that you needed about 3,300 degrees down here and 3,600 here to give you what was observed. That would give you a mean of about 3,600 degrees. Most interesting part to us was the correlation, and Graham showed this, between the pulsation. I mean, light's upside down. This bothers me. It always bothered me. Graham likes to body it that way. But so this is minimum light, and this is maximum interval. Notice they're correlated. And over here, even before it, they're correlated, similar to pulsating stars. The thing that's not showing, this is what was mentioned about critical changes, is that this could have been predicted if we'd known it before, because the oscillation, the radial velocity of the star on the 400-day period was going up. It was 2 kilometers per second back in here, 3, and then it went to 5. So then it reached its coolest part, dimmest part in the time of the Great Dimming. So this summarizes what happened, and Graham covered this. But I wanted to mention Levesque and Massey came out with the first paper on this in Astrophysical Journal Letters 891, 2020, where they claimed this couldn't have worked. But unfortunately, what happened is that they took the whole atmosphere of the star when they analyzed their data. So we were able to fit it because half of the atmosphere was dimmer. Andrea's going to, Andrea got an awful lot of press over this, 200 or so press releases all over the world in Chinese and so on, when she came out with her paper based on HST data. Blended HST images were obtained where you could see the a flare that took place. She called it, to me, the smoking gun, but she didn't want to go that far out, that smoking gun would be the dust. So this infers that there was a flare. This was a flare, and infers that maybe mass ejection took place. The mass was expelled, cooled, and then gives you the dust. Other papers were coming out, like we had, that were saying the star cooled down. You could get by because there was no evidence of dust except in the images and Miguel, that no dust was really needed. The portion of the star cooled, explaining it. This is Miguel's Nature paper. It's hard to kind of see where he's coming from here. He has a dusty veil shading Betelgeuse during its great dimming. Model explains the great dimming event, but he also is including stellar cooling in this. Maybe the stellar cooling triggered the cooling of the expelled gas. The images are beautiful, VLT images. Now, again, Constantino, how much time do I have?
I would say 5 minutes.
Okay, quickly, this is for an audience who would be attending the Marcel Grossman conference on, because this involves black holes, the end of days. I started to get, even though I did believe it was going to become a supernova, during this time in December, January of 2020, I started reading the press results and all that, and I started to contact, maybe it could. I was going crazy too. So I contacted Jim Fuller, who's an expert, and he sent me his paper where there is a burst, when there's a breakout that only lasts 20 minutes. It couldn't be that. And then he said, during the phase, the V-band brightness may decrease even if the volumetric magnitude increases. This is about a year before the event. So I was going, And then he was writing to Greg Wheeler. At the end, he's kind of said it was most likely, but then he said, nevertheless, be sure not to blink. So back to this supernova stuff. This is what happens when Betelgeuse or any red supergiant, large one, it forms it goes through various stages of burning, hydrogen to helium when it's an O star, helium to carbon, carbon to oxygen. This is kind of where it is now. But after that, it really takes off when it has this hydrogen, oxygen shell out in here. The burning takes 6 months. Silicon to iron is only 1 day, and then you have core collapse. So it really accelerates. So it'd be kind of, if it were in the end of the helium to carbon phase, it would only have 600 years to go only for it to blow up. Meredith's models indicate that it's in the early stages of that, meaning it's 100,000 years. So don't hold your breath. So this is the internal model prior to becoming a supernova. I really should skip this. I only had it in here for the, in case somebody doing black holes. I got really tied up on this. You have an iron core. The iron core collapses. You get inverse beta decay, a neutron. It has a shock. I'm just going through this real fast. Shock. The shock propagates through the star, less than the speed of light, and takes hours to get out, 2 to 3 hours to get to the surface. And then when it reaches the surface, you have this breakout where you have X-rays and ultraviolet radiation first, and followed by the rapid expansion of the whole star. This is when you see the supernova happen, and then 2 or 3 weeks later, it reaches maximum brightness. I was fascinated by this part that the gravity waves get out immediately. There's a gravity wave production when the core collapses. My colleagues at Villanova who work for LEGO said, yeah, we could detect it. It's near enough. We could detect the gravity waves from Betelgeuse if it did become a supernova. So I signed on to the LEGO alert list. And neutrinos were a snap. If it did go, you would see the neutrinos 2 to 3 hours after the core collapsed. So I joined, so I was going crazy here. I joined the SNU, snooze it's called, the early alert warning system for neutrinos. Of course, nothing happened. And I also joined the LEGO Virgo gravity wave alerts, thanks to my colleague. And the strange thing that happened in the middle of the night on, I had an attention, I had a beeper. And on the 15th of January, my beeper went off from the LEGO people that there was an alert that they saw something unusual in the direction of Orion, in the direction of Betelgeuse. Turns out it was false alarm, but I ran outside in the 2 in the morning in the rain, and I said, oh, drat, it's rain. And I have an hour or two before I could see anything. And then I gave up and went back to bed. It was false alarm. This is what would happen when it does blow up. Here's a nice winter night. And here's the Betelgeuse, the Radial, and all that. And blammo, almost as bright as a full moon. And to end this, what's up next? I got the supernova in. Okay, that was for the people attending the conference, which I don't think many showed up here, attending the major conference on our Marcel Grossman, black hole GR person. So here's the light curve now. This is the so-called great dimming. This is Andrea's observations with stereo. And here are the observations done. This is not ABSO. This is our observations with Rick. And I threw in here the daytime observations that Otmar Nickel got, which show the star to be rising. Interestingly enough, it's hard to know whether there's a paradigm shift. I mean, it has 3 pulsations, 3 dips, 1, 2, 3, but yet, going back, yet the star almost ended up, the bigger dip here, meeting the date line with the 420-day or 430-day period. It occurred just 15 days later than expected. So I don't know what that means. Is it going to, it will take more time. Is it going back to normal, to business as normal, or something changed here? And this is the new pulsation picture. So, and the post-great dimming is going on now. And the great dimming is a misnomer. I mean, other red supergiants dimmed more. As I mentioned, VY, Canis Majoris, W, Ceph had 2 magnitude changes, similar to Betelgeuse. But, Betelgeuse is a very bright star, and it just caught on. Will Betelgeuse return to business as usual, or increasingly unstable? Just dust, nothing to worry about, no structural changes, no dynamical changes are taking place. As Denis was talking about, critical transitions, what's next? Anyway, should continue to be observed. Multi-wavelength photometry is continuing. Stereo, I think Andrea might be talking about what's going on now. Daytime photometry is fabulous. Otmar, I didn't believe it before, and now it's wonderful. Now, because you miss a lot in those 100 days when Betelgeuse is hiding behind the sun. So that's fabulous that you can do it from the ground. and spectroscopy from Stella. This is a very important paper whenever it comes out. Thomas Grenzer has 10 years of data, spectroscopy and photometry, and it will actually shed an awful lot of light on what's going on. Andrea saw this coming, and she applied for HST UV time 3 years ago. She was prescient, so she caught the flare. This polarimetry, continued VLT, sphere, I hope, that's observed often, because that's what's needed, not just once a year like they usually give you when you're applying for time like that. IR, radio should all continue, and their facilities are reopened. So stay tuned, don't blink, and thank you.
You're very welcome, Edward, and also to show this image that I have the possibility to see all the evening, because I live,
oh, it's evening for you,
just
isn't it?
there.
Yeah.
So I enjoy that. I enjoyed your talk. I just make a small comment on the last oscillation you shown. It is very interesting, including the daylight data. I ask if it is the 185 period that was mentioned even by Meredith.
I didn't see it in that data. I was thinking that maybe the 185 would show up here. When I measured these, this was 160. I don't see it. It could be, you know, in there somewhere. I did check. Only time will tell. Maybe as this goes on, this might be 185. None of these period differences are 185. Although this difference between the one in February 2000 and in April does show up. I was kind of surprised. I thought at one point when I saw all this going on that the 430-day period was dead. And but I don't know. I mean, Betelgeuse has other variations other than the two I mentioned, or three I mentioned, 185, the 420 and 5. There's other things. If you look at the wavelet analysis, other periods just prop up from time to time. So only time will tell. And it's great that Othmar was able to, I just got this data. I added this yesterday, and I thought, as you see down here, Othmar, sorry, I thought Vin Moon did it. So I overwrote while I was in the middle of things. I gave you the proper accreditation. I have questions for him when this is over. So yeah, we do see the 185, 106-day period in our analyses when we have very good data. It's not a low, it's a lower level power, but it's still there.
Yes, I think he is still there. And before we obtain an answer, I want to remember to the speaker to send me the PowerPoint in view of the publication in the website, you know already. While there will be proceedings, as usual in Marcel Grossman, I read the first news. There are basically no limits, 20 pages, so it is possible to be wider in the proceedings. I don't know if Othmar wanted to say something. I just comment the real effort we did to observe Betelgeuse in the end of May, because it is impossible to see it. I have shown to you some photo, and that's why we observers, we talk together to compare our observation and so on. I would give the word to Andrea Dupri, and eventually leaving the last minutes to a round table. But Yes, I give the talk.
Before Andrea begins, I want to point out that Andrea and I have been observing Betelgeuse longer than anybody. But we started when we were in grade school.
I love it. No secrets, Ed. I want a secret. Come on, let me share my screen. Let me see what's happening here. Something is happening. Why isn't it? Oh, share. Sorry about that. It's coming. It's coming. Play from start.
Okay, we can see your screen.
Can you? I can't see my screen. Oh, there we go. Okay. Oh, wait a minute. I have the wrong one on it. I want the slideshow. Is it happening? There we go.
Yeah, it's good.
Yeah. Got it. Okay, but I have to go back. Back. No, I'm gonna go back. I'm going the wrong direction. Last. Sorry, gang. Let me go. There we go. Okay, I think I'm here. And I'll set my timer. So I'll have my 30 minutes. And as this has been going on, I've had to delete slides because you guys have shown everything I was going to show. So I've been taking them out bit by bit by bit. Constantino asked me to give a quote summary. So there's a little bit of summary and then a little bit of some very new results from 2 days ago. So I'm just going to keep you all informed of what's happening. All right, we know where it is, we'll skip that. But I also wanted to point out that 23,000 years ago, 17,000 years ago, if you go to the southwest of France and look in the Lascaux caves, which I have done, or at least seen the replica, there on the walls were the outlines of the Orion constellation, and there is Betelgeuse, and also the Pleiades and Taurus. All kinds of exciting things are there in the caves. And I think that beats some of the printed material we've heard previously. So that gives you another outlook on this. I also want to point out that 100 years ago, when they first measured the diameter of Betelgeuse, it made it above the fold in the New York Times, and they called it the Colossus of the skies. So even then it was recognized that this was a big, bright star and something to take note of. Okay, you've been through all of this, and I was very happy to see that Meredith's mass finally agreed, or my mass finally agreed with Meredith's 17 to 19 solar masses. We all know it's a red supergiant, a semi-regular variable, et cetera, et cetera. It's also big. It's bigger than practically every other star. You can see our little tiny sun there. This, I guess, is a French slide, and the Soleil is marked over there in the corner, and it's about 1,000 times the size of the radius of the sun. If you put it in the middle of our solar system, I always love this comparison, it almost reaches Jupiter's orbit. And this, of course, remember, is the optical diameter. And as we have discovered, and I will show you, the ultraviolet diameter is much larger, factors of 3 larger, which means that we are able to spatially resolve parts of the surface. Okay, the current state, we think it is now fusing helium into carbon, and it's an enormous red supergiant. Okay, and here I think is a similar figure that Ed just showed, that back in 1840 is when we sort of say it was the beginning of the visual estimates of the magnitude. And it was just bouncing along for the past 150 years or so, with this period on the order of 400 days, and then a longer period. Okay, I made back, oh God, a number of years ago, the first direct image of a surface of a star, which was Betelgeuse. And that is, we pointed the Hubble Faint Object Camera and took an image of the star in the continuum, which in itself was a challenge because we did it from the Space Telescope control room down at Johns Hopkins University. And they were so worried that we were going to burn out the faint object camera that they essentially started out with 5 neutral density filters. And they put the filter in and took an image, we read it down, we looked, we didn't see anything. So then they took out another filter, took an image, we still didn't see anything. Well, it turns out our predictions were fine. It worked out as predicted, but they were real worried. And the diameter in the ultraviolet is 3 times larger than the optical. And we did find this very bright, hot spot on one part of the star. The fact that it's larger than the optical, much larger, and the fact that there are small apertures on the Space Telescope, and we're doing this again from space, means that we're able, we have done this subsequently, and during the Great Dimming, we were able to actually resolve parts of the surface and look at the dynamics of the surface as this event occurred. Subsequently to the first imaging, we followed it for a number of years. This is just a sequence of ultraviolet images, and you see on the upper left, HZ4 is a point source, it's a white dwarf, and then the subsequent images spanning from t=0 to 4 years later show these are images taken with the same exposure times, and the sensitivity did not degrade. And so you can see that sometimes it's dim, sometimes there's a bright spot, sometimes the bright spot is bigger, smaller. We didn't get enough time to determine any period from this, but you can see there's clearly variability. And that's been documented in subsequent interferometric observations. There's a lot of infrared imaging that has been done, which has revealed these variable hotspots. On the left, there are 2 hotspots seen at 1 micron. There's a simulation. There are many simulations that have been done. And generally, folks can reproduce the size of these convective cells. They can be quite large. I mean, they can be up to half a stellar radius. They can reproduce the size of them, but not all the details. So that's still a challenge. And then we also can see that in the right, the Pioneer images show that indeed there are changes that they can document in the infrared. Now in the UV, as I said, we could use the apertures on the Hubble Space Telescope in order to sample across the ultraviolet image. And you see in the left various positions. This is with one of the larger apertures, but we could still sample 20, 30 positions. And then from that, looking at the spectra, we could determine the rotation and the angle of the axis of rotation. And that's where we first found that it was rotating rapidly for a supergiant star. And at that point, we speculated. We said, well, maybe it swallowed another star or maybe a planet, because planets had just been announced at the Cool Stars meeting in 1995, and planets were on everybody's mind. And I gather, though, later when people have done more quantitative calculations, that a planet wouldn't do it. It has to be another star. But anyway, we determined the direction of the axis, and at that point, one of the poles we saw was in the direction of the southwest, where there was an infrared plume that had been observed later. This orientation also agrees with the subsequent imaging by ALMA that Pierre Crivella has done. Okay, so here we go. the prescribed photoelectric photometer results from the AAVSO. And you can see trouble started around December 2019, I think, when Ed Guinan sent out a warning that, oh, it looks like things are going down. And then sure enough, February, in the middle of February, beginning of February, it hit bottom and then started to recover. Okay, and everything went crazy. I mean, we were at the AAS in Honolulu. We went out on outside the hotel, and nobody could believe what the constellation looked like. And what I really love was in Twitter, someone said, my calculations show that it's going to blow up tonight. So he wrote #hide. So I'm not quite sure where you hide, but I suppose it's good advice just in case. Okay, Klaus and Strassmeyer and Tom Granzer have been using Stella, which is on the Teide volcano in the Canary Islands for a number of years. It's an automated telescope, high resolution shell spectroscopy. And sure enough, they found a maximum outflow. This is radial velocity moving out is here, and the maximum outflow occurred in November of 2019. Now, I'm going to tell you the story of how we've constructed this after the fact, because now putting all these things together, and here I'm bringing in some new results, new observations, and some papers that perhaps you haven't noticed before. There's a technique called tomographic study, where one obtains an optical spectrum from Betelgeuse. This is unresolved. In other words, it's a star as a whole. And by studying individual lines and making models, we can understand where each line is formed, and lines of different strength are formed at different levels in the atmosphere. So by picking the proper lines, you can probe different parts of the atmosphere. And this was just published this year, and Catherine Kravchenko and colleagues determined that there were a succession of shocks in the photosphere between January and March 2019. It's perhaps not very impressive here, but this little blue shifted orange colored curve is what they saw happened at the lowest level of the photosphere. They have subsequently, this is just one of her images, which she interprets as shocks that are producing an expansion in the photosphere. And this happened in the spring, the northern spring, January to March of 2019. Okay, then we were fortunate enough to have the Hubble Space Telescope, where we could take a small aperture marked by this red rectangle and step it across the star. So we're stepping it across from the northwest, and we're doing 8 steps, 8 pointings across the ultraviolet image into the southeast. And we did this starting in January of 2019, all the way through April 2020. Particularly notable was the cloud of magnesium-2 line that we found in the south. Now on the left, I'm showing the flux of the magnesium-2 line as a function of position. So this is the northwest, this is the top, and you see that as you move over the center and the south during September, October, and November, there was huge enhancement of the magnesium. It wasn't there in March, and it wasn't there in February. So by February, when the optical light went down, the chromosphere was back to normal again. Okay, the optical diameter is indicated here. The UV continuum extends plus or minus 75 milliarc seconds out. So basically, in the fall, September through November, we did not observe in August. We did not observe in December. But during that period in the fall, there was an expansion of, the presence of a lot of magnesium-2 in one part of the star. Turns out we can look at the spectrum and we can determine that that cloud in the fall was of a higher density than the rest of the carbon-2 at different parts of the star. So there's more magnesium-2, it has higher density, and by looking at the magnesium-2 line profiles, they indicate its response to a traveling pulse of material going out over the southern part of the star. Okay, now that mass outflow, you see here's the radial velocity at the same time. Here's the maximum outflow velocity, and this is in the photosphere. And this is when we had the observations of the magnesium moving way out in the chromosphere, moving fast. And that is when the magnitude, this is September, October, the magnesium enhancement starts here, and then the star, then the star dims. Let's go back. Then the star dims. So clearly the dimming is following the maximum outflow velocity. So this led us to say that there was a confluence, there was a bright convective cell and motion combined to eject material, because this time coincided with the maximum outward radial motion. And you can see the change in the magnesium-2 lines shown here. And this is the press release at Hubble Space Telescope showing that there was something hot in the southern part of the star coming out. And this press release, as Ed said, went viral. I think our press people told us that 1.5 billion people had access to it, whether it was podcasts or the BBC or the Guardian or the New York Times or the Asahi Shimbun, whatever. It was everyone loved this idea. Okay, and then meanwhile, Miguel was taking or had taken a stereo image with the VLT, and this is in the continuum near the H alpha line. And you see in January, I think this has been shown before, in January there is a nice, relatively round, evenly illuminated star, and by December, the southern part was much darker. And this is the, whoops, sorry, let me go back. These are the sphere images that we published in Nature, which I think Ed and other people have shown, showing the change in January and then the recovery in March 2020. And his modeling suggests that dust is the culprit. The Space Telescope press people got very excited and produced lovely images saying that this is the place where it happened, and that what we saw in Hubble was the expansion of this chromospheric material that was sent out, got in the way of Betelgeuse and us, and condensed, the material cooled down, formed molecules, formed dust, and then the star was much dimmer. Okay. We've seen how there are gaps because Betelgeuse gets too close to the sun. And so we were amazed to realize that a satellite called Stereo, which is really a solar satellite, has a wide angle CCD camera. And this is a satellite that's in the Earth's orbit, but it trails the Earth by about 2.5 to 3 months. So that means that when we are in July, the satellite only thinks it's March or April, and it can observe Betelgeuse. And so we convinced them that it would be worthwhile to slew the satellite away from the Earth. They do this for an hour, they lose contact with it, and then they obtain 15 images of the field, the 70-degree field of view, and then we find other comparison stars that we can use. And that's where we found that indeed, after we lost it in the summer, we picked it up during June and July, and it was still getting fainter. Now there's another way of looking at it, and this is a very exciting result that Daisuke Taniguchi announced at the European Astronomical Meeting last week. He realized that there's a Japanese geostationary meteorological satellite that observes the Earth in a number of bands in the near infrared, but it also picks up the background to plus or minus 8 degrees across from the ecliptic, and that's where Betelgeuse is. So he went and he found Betelgeuse. See, here's the image that the satellite obtains. And if you look in the corner here, you see this little dot, and this little dot is Betelgeuse. So he then went on and filled in the past 4 years of Betelgeuse using this satellite. And you see here's the optical curve on the top in the green with the usual photoelectric results from the AAVSO. And then here's the Himawari data filling in the blank spots, which he has done from this meteorological satellite. But even more exciting, that satellite makes images in 16 photometric bands running from about 0.4 to 13 microns. And so what he's done in the right hand, I can't take you through this in glorious detail. So what he's done is these bands indicate Can it be used to interpret the temperature, the absorption of material, of dust, the reddening, the water vapor, all sorts of things. And so he finds that during the Great Dimming, which is marked by this broken line on the right, that when the magnitude went down, and he says here 1.2 magnitudes, the effective temperature went down, and also too there was increased reddening, increased absorption, visual absorption. So he's got a lot of data, and they're in the process of writing that up. But that's another way. I mean, in addition to Otmar's nice results of optical, of observing in the daytime with multiple images and things, if you get the right satellite, and by the way, we're checking the NOAA satellites. We think NOAA can do the same thing. So there may be hope that all of these stars that disappear from us on Earth, we can find in other ways. Okay, so what's happening now? It's brightening again. I have some data from stereo from 2 or 3 days ago, and two things here. First of all, here's the 420-day period, and you can see why we were so worried after the dimming and then the recovery in the spring of 2020, that it should have been bright again, but no, it didn't do that. It just kind of wobbled along. There's supposed to be another 420-day minimum. There should have been, not clear it's there, but it's starting to brighten again. So we shall see what happens. Will it come back on its 420-day pulsation? I don't know. Stay tuned. We have more Hubble time. We just won another 2 years of observing it, and we're going to try some new techniques with the Hubble Space Telescope. Okay, so what's the fate? Well, I said 100,000 years. Maybe Meredith would agree or not. Maybe the LIGO people will wake us up some night in the middle of the night saying it's coming, it's coming. The supernova, according to this calculation, will be as bright as the moon. It will cast strong shadows on the ground, and you can easily see it in full daylight. So that's something to look forward to. So we need to enjoy this star while we can. Thank you.
Thank you very much, Andrea, for this wonderful presentation, also for this splendid map. I knew the image of Lescaut, but I didn't know, after reading your abstract, I knew, but before I didn't know that it was representing the stars.
I know, it's amazing. Now I've lost, I'm going to stop sharing, see if I can get you back. There we go, okay, yeah.
I have an immediate question about the minima of Betelgeuse, especially after having seen the satellite integration. So we have at least 4 years without any gap. So the question is, why the minima are all V-shaped?
I don't have an answer.
The question is in this way because we know, for example, the eclipse variable stars, and they can show a bush shape, a V shape because of the geometry. But why? This question was coming from the observation, so I could see the V observation of Wolfgang Wollmann, and they were always V-shaped, but the maxima were not clear because apparently they occur just in the gap of the sun.
I don't know, maybe that could be predicted from the pulsation. I mean, if folks who predict the pulsation characteristics of that. I haven't looked in detail. I don't have an answer for you.
Constantino, they're really not V-shaped when you stretch them out on a
it depends on your plot.
Yeah, on a very scrunched plot where you're taking 50 years of data, they look V, but when you take them years, they turn out to be not so much.
Here you go. Okay.
It's perspective. I know you're thinking of, you want to have clouds of dust, those dimmings, I think. Is that right?
Me?
No, Constantino, I think.
I agree on what you are saying, because In February last year, I was trying to guess the minimum by analyzing with a parabola the visual data or the data available from AABSO. And yes, if we look on the scale time of days, you don't see the V.
What I found very interesting when people were questioning whether dust could form that quickly is if you look in the literature of these other stars called our corona borealis stars. These are stars that are yellow supergiants, and they show very fast, rapid outflow of material. When I say fast, I mean 100 kilometers per second. I mean, we don't see that, but very fast outflows. And then within a day, the magnitude can drop like 8 magnitudes, 9 magnitudes. I mean, down like a stone. So, I mean, this can happen. So that's our favorite theory. And now that we have the tomographic work that Katerina did, showing the shocks in the photosphere and the moving out, then we captured it in the middle. But by the time it got out to the place where it cooled down and molecules and dust formed, the photosphere was normal, or hot or cold or something like that. Say, but it also introduces a lot of other questions, like what happened to the star afterwards? Because remember, if we look at coronal mass ejections, which we see a lot in the sun, what happens is the magnetic field reconnects, material is thrown out, and then suddenly there's a low density region, low pressure region, cooler region left in the photosphere sometimes of the sun. So what is the effect? The other question we have is, are we going to see things at coming from different parts of the star? I mean, there's been infrared plumes from one axis, and ALMA has measured silicon oxide from another axis. But when you look at stars like VW Canis Majoris, and you look at the surrounding material, you see that material has been shot off in all directions, not just from preferred directions, like the axis of rotation, okay? So the question is, and we have a hint from our Hubble observations, that was going more to the southwest, than the southwest and the southeast. I have to think maps, and then I have to think right ascension and declination at the same time. And so, but we seem to see it going off at a different angle from where the axis of rotation is. So there are a lot of interesting questions, and I think we're having the spectroscopy. We just won 2 more years of Hubble time, and we're going to try doing the tomographic work in the ultraviolet. We know that there are about 600 lines that we can use there, and we're going to be able to go across the surface of the star and obtain spectra, and then pick the right lines from different levels, and not only get the spatial resolution for the very first time, but also a depth resolution. So I hope it misbehaves. That's all I can say. Fingers crossed.
Well, we have nominally other 20 minutes to the shutdown of the system. And since there are many people potentially interested in doing some discussion, I encourage you to propose. Since I'm obviously sure that I will forget to say the appropriate thanks to the speaker, I say these thanks now, also on behalf of the organizers of the Marcel Grossman meeting, namely Professor Remo Ruffini. He wanted this session on Betelgeuse. It was his own idea. And so he thanks you all for participating in this very nice presentation. So this is for avoiding to forget it at the last moment. I don't want to also to profit of your resistance, but I think we had a series of presentations in which we have a good balance between observations model, theory, analysis, like Fourier analysis and time series analysis. At the end of this many presentation, the idea is, to quote some title, the dust is settled, or we are dealing with some convection of the star. I mean, the change of temperature can explain everything. The dust and the change explain together the things. Because before projecting this parallel session, it was not so clear that the dust was not the responsible, especially also looking in the form of the meaning.
That's the plot. Yeah, well, I think there was a confluence. We have to assume that there was a hot convective cell on the surface, and these things can be big. I mean, really, they can occupy half the surface of the star. Okay, that comes from the models, it comes from the imaging. We also have the photospheric evidence that something was going on. There were shocks in the photosphere in January through March of 2019. Okay, and then we see the stuff moving out through the chromosphere in the fall. We see the dark part, the dark southern hemisphere in December and February, and you know, I think it makes a strong argument that the spectroscopy has really helped us. There's also polarization measurements, which we haven't mentioned. That the Russian group had measured polarization changes, which is what one would expect from dust. So just hope it does it again. See, that's what we need.
Another question that arises from the last yesterday session, plenary session of the Grossman meeting. We had some presentation by Wendy Friedman, who spoke about the key project of HST, Hubble Space Telescope, for the definition of Hubble constant. The question is, I'm sorry that in this moment Meredith came in distance of the computer, but about the parallax of Betelgeuse, so the precise measurements of its distance, the new parameters that we have on the distance, on the dimension of the mass of these stars can be measured directly instead of only theoretically or by model. So my question was on the parallax of Betelgeuse, since we had examples of very precise measurement done with the Hubble Space Telescope for the Hubble constant. Now Betelgeuse is much more close. Are possible measurement of its parallax to prove the models? I open the question also to Meredith, to everyone.
Well, it's hard to measure the parallax. I know that with Hipparchus, the problem is that because of the surface of the star changes in brightness, like you get a hot spot on one side, a hot spot on the other. That's why the Hipparchus result, the original result, was deemed unreliable, because it was hard to get a center of light. You didn't know quite where the center was. Right, Graham? I mean, you were dealing with a lot of that as well.
Yeah, I mean, the original Hipparchus reduction, it turned out to not very good. And there was the revised parallaxes from Van Leeuwen. And the error bars on the parameters came down. And then what happened is, for Betelgeuse, the Hipparchus solution was completely discrepant with the radio data. And I think what people forget is the parallax solution is a 5-parameter solution. It's 2 positions, 2 proper motions, and a parallax. They're all solved simultaneously, and we know from the radio, irrespective of the size of the star and the photocenter, the proper motions are incorrect. So we know there's a problem with the existing Hipparchus data. just because the parallax looks similar to what Meredith got is purely, that's just happenstance. Because the radial velocities you can measure, it's a large proper motion star, right? So it's moving 25 milliarc seconds a year. You measure over 30 years. It doesn't matter where you are, the radial proper motions are incorrect from Hipparchus. And that's why, you know, our solution was never going to get any better. So it's tough. So I think, you know, I think if Meredith's technique can be benchmarked on some other objects, I think that's the way we're going to get the best values for the distance. That's my personal opinion, worth 10 cents.
I invite everybody to give me 100 or 200 year longitudinal light curves for every star there is out there, so I can see if what I do gives consistent results for more than one candidate. I mean, I'm not an interferometrist myself, but I worked with Mike Ireland on this, and something else that came up that would affect both of these distance determination methods is that the apparent size of it is very different depending on what waveband you're observing, and then there's all kinds of complexities. So I mean, even so, the interferometric observations were necessary for my prediction of the distance as well, but I think there's some complications in there that are, I don't know, maybe somebody else could speak to this, like whether it's the actual parallax or the interferometric measurements are providing more uncertainty.
The other thing is it's not always spherical, depending on what lines you're looking at.
The details that Hubble Space Telescope shown on the surface of Betelgeuse are not so different from the ones shown on Myra. So practically nothing very, very clear except some bright or dark spots. What do you expect for the future, knowing what you said in your talk, that Betelgeuse is so luminous that can burn the detectors? But about resolution, where we can go?
Well, I think things like ALMA are doing amazing results. And we also have some Chara time coming up with one of their new detectors. So hopefully we can approach it in different ways. We'll see. We'll see.
You or Edward presented the diameter of Betelgeuse in 1920s.
It's pretty good. That's the optical diameter. They measured by putting beams out on Mount Wilson, the telescope, and used, you know, an interferometer. Basically, got fringes, and they got, I think, 42 milliarc seconds, and that's pretty good right now.
It is the diameter in one direction, or they did in
one direction.
It is possible to replicate something like that with some modern telescopes.
Well, ALMA can construct an image with the VLA, you know, not the VLA, ALMA. In other words, and you get different baselines and different directions, but you also have to make assumptions. You have to make assumptions about limb darkening, and you have to make and I don't know how much you're affected, but I'm sure you are, by bright spots or asymmetries. I mean, it's not easy.
We have the image of central active region of M87, and we don't have an image of such resolution of Betelgeuse. We should have.
Okay, well, we've been patient. We've been sitting here for 4 hours, 5 hours, 4 hours.
Yes, it has been a very long session. I want to thank all the speakers and all the attending people. And more of them are also active observers and astronomers or students, colleagues. So let me thank every one of you to have attended this special session dedicated to Betelgeuse and to its historical dimming or fading, according to the best definition. And yes, the talk will be available in the first version. So the version I have registered, you will see in this web page, let's say in few hours. The web page I can send you. This one, I send the web page by chat. In the same web page, I wish to include also the PowerPoint, the presentations. In some days or weeks, you will receive the instruction for the proceedings. As you said all in your presentation, stay tuned because Betelgeuse is coming back, even to the visibility for the naked eye. In few weeks we can start to see again in the morning sky. So I hope to have answered to your question. I'm sorry to have not to have no more time, because they will cut the presentation. So thank you very much to every one of you. Really thanks for having accepted to participate to this special session.
Okay, bye-bye.
Goodbye.
Thank you.
Thank you.
Bye.
Bye.
Goodbye, Graham. Thanks.
Grazie, Costantino.
Prego, grazie. Thank you, Wolfgang.
Bye, Ed.
For participating.
Goodbye, Graham. We'll be in touch. Meredith, too. Bye-bye.
Goodbye.
Bye.
Goodbye.
Bye-bye.
The registration will be stopped by the organizers, so we do our stop, but not. Oh, Rod, is the sun coming out there? I see the light in your room, but I don't see you. I don't hear you. You have to. No, you speak, but we don't hear. Well, problems of audio. Anyway, thank you very much to have participated, and I'm sure that you found interesting arguments in this talk. Ciao, professor Palagiano.
Ciao, Costantino.
Grazie di aver partecipato a questo.
Ho imparato tante cose.
Anch'io.
Tutte cose, anche per esempio di quell'Atlante che mi è molto interessato, quello di Flamsteed, storico dell'Atlante celeste.
Strano, perché quell'edizione che lui ha mostrato del 1000, Flamsteed è di un secolo prima. Lui è di un secolo prima, perché se non mi sbaglio, ma forse mi sbaglio.
No, il 1776.
Sì, ma lui era precedente.
Sì.
Era forse del secolo precedente.
Sì, sì.
Quindi quella è un'edizione molto...
quel lavoro che voglio fare, polar, eccetera, extraterritorial business. Va bene.
Lorenzo, puoi comparire se vuoi, non te mangiamo.
Sto qui.
No, c'è Lorenzo nascosto nel...
Allora, buonasera.
Carissimo.
Come state?
Abbiamo fatto questa maratona, veramente, roba da mal di testa, perché Cioè io devo guardare lo schermo del computer con massima attenzione da vicino e dopo 3 ore comincia a girare la testa.
Certo, sì.
Comunque.
Beh, no, tutto bene, dai.
Sì, è stato un ottimo giro di presentazioni. Forse ci potevano essere più domande e risposte, ma quelle ci saranno.
Beh, l'importante è che l'abbiamo salvata, così poi possiamo rivederla, posso rivederla. L'importante è quello, no?
Ma io penso che molti studenti utilizzeranno poi questo.
Ma speriamo. È materiale utile comunque.
Come source. Va bene. Allora, grazie a tutti. E lasciamo il campo libero agli organizzatori per finire la registrazione.
Grazie ancora a lei, professore. Arrivederci.
Ciao a tutti. Ciao.